Right now, while you're lying here, while your breathing is just beginning to slow and the weight of the day is finally starting to loosen its grip on you, there is a place inside our own solar system where it has been night for 4.5 billion years. Not the soft night of a bedroom with the lights turned low, not the gentle night of a quiet street after midnight, a different kind of night, a night that has never once been interrupted by a sunrise, a night so old that it began before the earth had finished forming, before the first ocean had cooled, before the first living cell had ever divided. That place is not in some distant galaxy. It is not light years away. It belongs to us. It orbits the very same star that warmed your skin this afternoon, the same star your ancestors watched climb the sky for 100,000 generations. And yet, if you could somehow stand on the surface of one of the frozen worlds that drift through that region, and you tilted your head back to look for the sun, you would have to search for it. You would find it eventually. It would still be the brightest thing in the sky. But it would not be a disk. It would not be a warm golden circle hanging above you. It would be a single, sharp, brilliant point of light, a star among stars, no wider to your eye than the tip of a needle held at arm's length. It would give you light. It would give you almost nothing else, no warmth, no comfort, no sense that you belong to anything. This is the story of that place. It is a region so vast, so cold, and so quietly enormous that learning about it for the first time does not feel like adding a fact to what you already know. It feels like discovering that the house you have lived in your entire life has an entire wing you never knew existed. A wing stretching off into the dark, room after room after room, far larger than the part you thought was the whole. Scientists call it the Kuiper Belt, and almost everything you were taught about the edge of the solar system is about to come apart. So let yourself settle. Let your shoulders drop away from your ears. Let your hands rest open and easy. There is nothing you need to do for the next little while except listen and drift, and let your mind wander out past the last familiar planet into the long, slow dark. We're going to travel a very long way from here tonight. Before we leave the warmth of the inner solar system behind, let me ask you one small thing, and you do not even need to open your eyes to do it. If you find a strange kind of peace in journeys like this one, in slow, quiet voyages through the cold and the dark that somehow make the world feel softer rather than smaller, then take a moment to subscribe to Deep Space Slumber and gently tap the like button before you drift off. It is a small gesture from you, but it is the thing that lets these long nighttime journeys continue, and it helps other restless minds find a calm place to land when sleep will not come easily. That is all. No urgency, no rush. Just a quiet thank you from me to you before we go. Now, get comfortable. Pull the blanket a little higher if you need to. And let us begin at the place where almost everyone believes the solar system comes to an end. The solar system does not end at Neptune. It does not even come close to ending at Neptune. This is one of those sentences that sounds like a small correction, a minor footnote, the kind of thing a teacher might mention briefly before moving on. It is not a small correction. It is the difference between a map of a single room and a map of an entire continent. Because what lies beyond that last blue planet is so enormous, so physically extreme, and so badly represented in almost every picture of the solar system you have ever seen, that absorbing it properly rearranges your sense of where you actually live. Picture for a moment the solar system as you learned it. The sun in the center, glowing. Then the planets, set out in a tidy line. Mercury, small and scorched, hugging the sun closely. Venus, wrapped in its suffocating clouds. Earth, the pale blue one, the one with us on it. Mars, rust-coloured and thin-aired. Then a gap, and the four giants. Jupiter with its great storm, Saturn with its rings, Uranus tipped on its side, and Neptune deep blue and remote, the last one in the row. And then the picture stops. The poster ends. The diagram has a border, and Neptune sits near the edge of it, and the empty white space beyond the border is, in the imagination of almost everyone who has ever looked at such a diagram, simply nothing. The end. The outer wall of the solar system. That outer wall does not exist. Beyond Neptune, the solar system keeps going, and it does not keep going as a thin trickle of leftover dust. It keeps going as an entire structural region, a broad, deep, three-dimensional zone populated by an immense number of frozen worlds, a region so wide that the familiar planetary system, the one with all the famous names, fits comfortably inside its inner third. Let that settle for a moment. The solar system you were taught, every planet you can name, every world that has ever appeared on a magazine cover, every place a spacecraft has ever photographed. All of it occupies roughly the inner third of the Sun's true domain. The rest, the larger part, the part that almost no one ever describes in any detail, begins right where the familiar picture ends. That larger part begins with the Kuiper Belt. Start with the simplest possible description of it. The Kuiper Belt is a broad donut-shaped zone of icy bodies. It begins out near the orbit of Neptune and extends outward from there into the dark. To talk about it sensibly, we need a unit of distance, because the numbers involved are far too large for kilometres or miles to mean anything to a human mind. So astronomers use the astronomical unit. One astronomical unit is simply the distance from the Earth to the Sun, about 93 million miles, or roughly 150 million kilometres. It is already an enormous distance. Light itself, the fastest thing in the universe, needs about 8 minutes to cross it. Neptune orbits the Sun at about 30 astronomical units, 30 times the distance from the Earth to the Sun. The Kuiper Belt's main body begins right around there, at 30 astronomical units, and stretches outward to at least 50, and the most scattered, most far-flung members of its family reach far beyond even that, out to 70, 80, 100 astronomical units, and more. These are not numbers that have been adjusted to look dramatic. They are not exaggerations for the sake of a story. They are simply the measured dimensions of the place, and they are so large that they quietly break every instinct a human being has about distance. Try to feel it this way. Imagine you could drive a car toward the inner edge of the Kuiper Belt, a perfectly ordinary car, travelling at a steady highway speed, never stopping, never slowing, never running out of fuel. To reach the inner edge of the Kuiper Belt from here, you would need to keep that car moving at highway speed without a single pause for more than 5,000 years. 5,000 years of continuous driving. The whole of recorded human history from the first written word to this very night would not be long enough for the trip, and to reach the outer edge, you would need to keep driving for roughly another 2,000 years beyond that, and the entire time you would be driving through absolute darkness, through a vacuum, with the sun shrinking in your mirror until it was no longer a sun at all, just a bright and lonely star receding behind you. But the raw distance, as staggering as it is not the part that truly unsettles people. The part that truly unsettles people is what the existence of the Kuiper Belt does to the proportions of the solar system, to the shape of the thing, the balance of it, the sense of how much of it you were ever actually shown. Let us walk the familiar part of the solar system first, slowly, so the comparison lands properly. Mercury orbits the Sun at roughly 1/3 of an astronomical unit. Venus at about 7/10, Earth, by definition, at 1. Mars at about 1.5, then the long quiet gap, and Jupiter at a little over 5, Saturn at about 9.5, Uranus at just past 19, and Neptune at 30. So the entire procession of planets, every world you've ever seen named on a diagram, the rocky ones and the gas giants alike, from scorched little Mercury all the way out to deep blue Neptune, spans about 30 astronomical units. That is the width of the solar system as it lives in the human imagination. 30 units, from the Sun to the last planet, the whole show. Now look at the Kuiper Belt. Its main body alone runs from 30 astronomical units out to 50. That is 20 astronomical units of additional structure. 20 units of solar system that almost no one ever pictures. To put it plainly, the main belt on its own is 2/3 as wide as the entire span of the planets. It is bolted onto the end of the solar system like an enormous unlit room appended to a house, and most people have never heard it described in any real detail. And if you include the scattered eccentric members of the Kuiper family, the objects that swing out on long stretched orbits far beyond the main belt, then the Sun's icy outer realm reaches to 100 astronomical units, and in places further still. Hold those two numbers side by side. The planetary system, 30 units across. The icy outer realm, at least as wide and very likely far wider. This is the fact that rearranges the picture. The solar system you know, the rocky planets, the gas giants, the rings of Saturn catching the light, does not sit at the centre of the Sun's domain with the edge a short distance beyond Neptune. It sits crowded into the inner third of something much, much larger. Everything past Neptune is greater in sheer reach than everything inside it, and almost nobody ever talks about it. I want to be very clear about something here because it matters. This is not fringe science. This is not a speculative idea hidden away in obscure journals, waiting for proof. The Kuiper Belt has been a confirmed, mainstream, thoroughly studied part of solar system science for more than 3 decades. It is as real and as solid a feature of our cosmic neighbourhood as the asteroid belt, or the rings of Saturn, or Jupiter's great red storm. The only thing strange about it is how completely it has been left out of the picture that most people carry in their heads. Ask yourself a simple question. How many times in your life have you seen a diagram of the solar system that showed the Kuiper Belt at its true scale? Not a faint dotted arc tucked into the corner of a poster. Not a tiny grey smudge with the label too small to read. An honest, proportional depiction, showing this region as the vast outer realm it actually is. For almost everyone, the honest answer is never, not once. And that absence is not harmless. It quietly teaches billions of people a distorted version of their own home. It tells them the solar system is a neat row of planets, with a clean edge a little past the last one. It lets them believe the place has been mapped, explored, finished, that the story is essentially complete with only the small print left to fill in. But the story is not complete. Out past Neptune, it is barely begun. If you were to draw the planetary zone honestly, to scale alongside the Kuiper Belt, the 8 familiar planets would huddle together near the centre, a bright and busy little cluster, and then the icy belt would sweep outward around them, twice their combined reach or more. the solar system would stop looking like a tidy line of worlds. It would start to look like what it actually is, a small, warm, brilliant core surrounded by an enormous, frozen, mostly empty halo. That halo is where we are going. But to truly understand it, we first have to understand how anyone ever found it at all. Because for 40 long years, the Kuiper Belt was nothing more than a guess, an idea, a faint hope held by a handful of astronomers who could not prove it was there. The idea came first. The idea always comes first. In the early 1950s, a Dutch-American astronomer named Gerard Kuiper turned his attention to the outer solar system and asked a quiet question. In the beginning, when the sun was young and surrounded by a great rotating disk of gas and dust, that disk surely did not simply stop at the orbit of the last planet. It must have continued outward. So what happened to all the material that lay beyond Neptune? What became of the icy debris in that outermost zone? Kuiper proposed that a disk of small, icy bodies could indeed have formed out there, early in the solar system's history. As it happens, his own reasoning led him to suspect that this disk had long since been scattered away and emptied out, that it was not there anymore, but the central image, the idea of a population of icy worlds beyond Neptune, became attached to his name. And he was not alone. A few years earlier, an Irish astronomer named Kenneth Edgeworth had independently speculated about much the same thing. A reservoir of small frozen bodies orbiting in that distant region, leftover seeds of creation that never grew into a planet. Because of his contribution, the region is sometimes called the Edgeworth-Kuiper Belt, a name that quietly honours both men who imagined it before anyone could see it. But imagining a thing is not the same as finding it. And for 40 years no one could find it. For 4 full decades after these ideas were first put forward, the outer solar system stubbornly refused to show anyone what it contained. As far as the telescopes of the time could tell, there was exactly one object out beyond Neptune, Pluto, discovered in 1930. And Pluto was treated as a lonely outpost, the 9th planet, the final world, a single small light sitting by itself at the cold edge of everything. The idea that Pluto might be just one member of a vast hidden population was considered reasonable. It was also considered completely unproven, and likely to stay that way. The problem was not a lack of imagination. The problem was light, or rather, the heartbreaking lack of it. The objects of the Kuiper Belt are small, and they are dark, and they are almost unimaginably far away. They produce no light of their own. They can only shine by reflecting the feeble glow of a sun that, at their distance, has shrunk to a brilliant point. An object out there might be hundreds of kilometers across, a genuine little world, and still appear in even the finest telescope as nothing more than a single faint, trembling speck, barely separable from the background darkness, drifting so slowly against the fixed stars that you would need hours or whole nights of patient watching to be sure it had moved at all. To find such a thing, you would have to photograph a small patch of sky, deeply and carefully, and then photograph the exact same patch again hours later, and then compare the 2 images dot by dot, looking for the single point of light that had shifted position. A point that moved was an object orbiting the sun out in the dark. A point that stayed still was just another distant star, and you would have to do this over and over and over, with no guarantee that anything was out there to find. 2 astronomers decided to try anyway. In 1987, David Jewett and Jane Liu began a deliberate systematic search for the theoretical belt, working from the great telescopes high on the dormant volcano Mauna Kea in Hawaii. The task in front of them was almost cruel in its difficulty. They were hunting for objects so faint they hovered right at the very limit of what their instruments could detect, points of light millions of times dimmer than anything the unaided human eye can perceive. And they had no promise, no assurance whatsoever that a single one of those points existed. So they did the work, night after night. They took their deep exposures of small fields near the plane of the solar system, where such objects ought to live. They compared images taken hours and nights apart. They searched for the dot that moved. And for years, nothing moved. The early results were not just disappointing. They were the kind of results that make a person wonder if they have devoted a piece of their life to chasing something that was never there. The outer solar system, as far as their patient searching could tell, appeared to be exactly what the old conventional wisdom had always insisted it was: empty. 5 years of searching produced 5 years of silence, 5 years of faint, still, stubbornly motionless stars. And then came the night of the 30th of August, 1992. On that night, in the comparison of their images, there was a dot that had moved. It was faint, almost impossibly faint, barely there at all, even in their long, deep exposures. But it had shifted against the background of stars, and it had shifted at exactly the slow, deliberate rate you would expect from something orbiting the Sun at roughly 44 astronomical units. 44 times the distance from the Earth to the Sun. It was not an asteroid wandering out of the inner solar system. It was not a comet streaming toward the warmth. It was not a known moon, and it was not a known planet. It was something new, an object of an entirely new kind, orbiting in the precise region of space where the theoretical belt had been predicted to exist 4 decades earlier by men who never lived to see it confirmed. They gave it a designation. In the formal language of astronomy, it was called 1992 QB1, and that single, faint, slow-moving speck pried open a door that could never again be closed. Because once you've found one, the search changes completely. You're no longer wondering whether anything is out there. You know something is out there. You're simply finding the rest of it. Within months, Jewett and Liu had found a second object, then a third. Other teams, hearing the news, turned their own telescopes and their own survey programs toward that distant zone. Cameras grew more sensitive. Telescopes grew larger. Search strategies grew sharper and more dedicated, and the outer solar system, which for 40 years had shown the human race nothing at all, began, slowly at first, and then in a flood, to reveal what it had been holding all along. The faint specks appeared one after another in the data, dozens, then hundreds, each one a small frozen world, drifting silently in the dark beyond Neptune, every one of them having orbited there, unseen and unsuspected, for the entire history of human astronomy. Every star chart ever drawn, every map of the heavens from every ancient civilization, every careful catalogue made by every astronomer who ever lived before 1992, all of them had simply left out an entire population of worlds, not because anyone was careless, but because no instrument on Earth had been able to see them. The Kuiper Belt went, in the space of a single decade, from theory to undeniable fact, and the scale of what was uncovered kept growing. As of today, astronomers have directly catalogued more than 3,000 individual Kuiper Belt objects, but the catalogued ones are only the visible tip of something far larger. The models, calibrated against the surveys, suggest that the belt contains more than 100,000 objects larger than 100 kilometers across, 100,000 bodies, each one large enough to be called a small world in its own right. And if you count downward to objects merely a kilometer or so across, the total population runs into the hundreds of millions. The Kuiper Belt is not a sparse scattering of a few stray rocks. It is one of the most heavily populated structural regions in the entire solar system. It contains more individual objects than the famous asteroid belt between Mars and Jupiter, and it occupies a volume of space so enormous that the entire asteroid belt could be tucked inside it thousands upon thousands of times over. And yet, if you stopped 100 people on the street and asked each of them to name the major regions of the solar system, almost all of them would say the inner planets, perhaps the asteroid belt, the outer planets, and then they would stop. The Kuiper Belt would barely register. It lives in a strange blind spot in the human mind, fully acknowledged by science, thoroughly studied, completely real, and yet almost entirely absent from the picture that ordinary people carry of their own cosmic home. So let us begin, properly, to fill that blind spot in. Let us go and see what is actually out there. To understand what makes the Kuiper Belt so profoundly different from anything in the inner solar system, it helps to first understand the asteroid belt, because the two are often spoken of in the same breath, as though they were simply two versions of the same thing. They are not. They're not even close. The asteroid belt lies between the orbits of Mars and Jupiter, at roughly 2 to 3.5 astronomical units from the Sun. It is the region most people picture when they imagine a belt of debris, a crowded field of tumbling rock, the kind of place a spaceship in a film must weave through at high speed to avoid being smashed. The reality is far gentler and far emptier than the films suggest, but the composition is the important part. The asteroid belt is built of rock and metal. Its bodies are made of silicate minerals, of iron and nickel, of materials that can hold together as solids, even in the relative warmth of the inner solar system, where the sun still shines with real strength. The largest object in that belt, Ceres, is about 940 kilometers across, large enough that it has been reclassified as a dwarf planet in its own right. But the belt as a whole is surprisingly slight. If you gathered up every asteroid in it and weighed them all together, the total would come to only about 4% of the mass of our Moon. For all its dramatic reputation, the asteroid belt is sparse, lightweight, and made of stone. The Kuiper Belt is a different creature entirely. Its worlds are not built of rock and metal. They are built overwhelmingly of ice, and not only the kind of ice you know. Water ice is there, certainly, but out in the Kuiper Belt the cold runs so deep that substances we would never think of as solid become solid too. Methane, the gas that burns on a kitchen stove, exists out there as ice. Ammonia freezes hard. Carbon monoxide, a gas here on Earth, locks itself into a crystalline frost. And nitrogen, the gas that makes up 78% of every breath you've ever taken, the most ordinary, invisible, unremarkable air imaginable. Nitrogen, in the Kuiper Belt, freezes into a pale, translucent solid. This is possible because of how cold these worlds are. The surface temperature of a typical Kuiper Belt object hovers somewhere around 220 to 240 degrees below zero on the Celsius scale. That is a cold so extreme it is difficult to even call it a temperature in the way we usually mean the word. It is closer to a kind of stillness. At that cold, the restless jostling of molecules, the constant trembling motion that warmth really is, slows almost to nothing. Substances that flow, drift, and evaporate anywhere near the sun simply stop. They settle, they harden, they become the bedrock of these distant worlds, and those exotic ices are not an incidental detail. They are the defining feature of the Kuiper Belt, and they are also the reason it matters so deeply to the people who study how the solar system was born. Because the frozen materials out there are not random, they are leftovers. They are quite literally the unused building blocks of creation. Cast your mind back 4.5 billion years. The sun has just formed, a young star surrounded by an immense, slowly rotating disk of gas and dust. The solar nebula, the raw material from which everything else would be made. Close to the young sun, where it was hot, only rock and metal could survive as solid grains. Everything more volatile was driven off as vapour. Those rocky grains over long ages collided and stuck and clumped and grew, and in time they became the small, dense worlds of the inner solar system: Mercury, Venus, Earth, and Mars. Farther out, past an invisible boundary that astronomers call the frost line, the disk was cold enough that ices could freeze and survive alongside the rock. There was simply far more solid material available out there, because now the ices counted too. And so the worlds that grew in that colder region grew enormous. Jupiter, Saturn, Uranus, and Neptune, the giant planets, each one gathering a vast envelope of gas around a heavy core. But out beyond the last giant, something different happened. Or rather, something failed to happen. In that outermost region, the disk of material was simply too thin, too sparse, and the orbits too slow and too long for the building blocks to ever gather themselves into a true planet. The pieces were there, the raw material was there, but it never assembled, it never finished. It stayed scattered, countless individual frozen chunks, drifting in slow wide circles, waiting for a planet that would never come. Those chunks are the Kuiper Belt objects. They are construction material that was never used. They are the leftover bricks of a planet that the solar system started and then abandoned. And that is exactly what makes them so extraordinarily precious to science. Because they were never used, they were never transformed. A planet, once it forms, is melted and stirred and reshaped by heat and pressure and time. It forgets its own beginnings. But the Kuiper Belt objects were left alone, out in a deep freeze so profound that almost nothing has changed them. They have been preserved for 4.5 billion years in a state remarkably close to their original condition. They are fossils, they are time capsules, they are samples of the original recipe of the solar system, kept in cold storage since the day the sun first lit. To study them is to read the ingredients list of a meal that was cooked and eaten an unthinkably long time ago, except the ingredients are still here, still raw, still waiting. But there is a complication in this gentle picture of preservation, and it is a complication that makes the story far stranger and far more interesting than a simple tale of frozen leftovers sitting quietly in place. The Kuiper Belt has not simply sat still since the solar system was born. It has been moved, it has been stirred, scattered, sculpted and rearranged, and the hand that did the stirring belonged to a planet. It belonged above all to Neptune. Here is the thing that surprises most people when they first hear it. The giant planets did not always orbit where they orbit now. In the early solar system, they sat in different places, closer together, more tightly packed, arranged in a more compact configuration than the wide and stately spacing we see today. And then, over a long stretch of the solar system's youth, they moved. They migrated. Jupiter drifted slightly inward. Saturn, Uranus, and Neptune all drifted outward, away from the Sun. Neptune's outward journey was the most dramatic of all. As it slowly migrated outward, Neptune ploughed directly into the primordial disk of icy bodies, the original far denser ancestor of the Kuiper Belt. And as it advanced, its gravity reached out and seized every frozen body it came near. This is where the architecture of the modern belt was carved. Neptune's gravity did not treat every object the same way. Some bodies it flung inward, hurling them toward the Sun. Some it flung outward, casting them onto long, stretched, eccentric orbits far from the main belt, and some, a great many, it captured, locking them into a particular kind of stable rhythm called an orbital resonance. A resonance is one of the most elegant ideas in all of celestial mechanics, and it is worth pausing on, because it explains so much of what the Kuiper Belt looks like. A resonance happens when two orbiting bodies fall into a simple, repeating relationship, when their orbital periods form a tidy whole number ratio, so that they meet each other and tug on each other in the same gravitational rhythm again and again, forever. That repetition, instead of slowly destabilizing the smaller body, can actually protect it. It can lock the smaller body into a safe, stable path that keeps it forever away from a dangerous close encounter with the giant. The most famous resonance in the Kuiper Belt is the 2-3 resonance with Neptune. An object caught in this resonance completes exactly 2 orbits around the Sun for every 3 orbits Neptune completes. That precise lockstep stabilizes its path and shields it from ever colliding with Neptune, even though their orbits cross. And the most famous object caught in that resonance, the most famous resident of the entire Kuiper Belt, is Pluto. Pluto is not alone in that resonance. It shares it with hundreds of other icy bodies, all of them dancing the same 2-3 step with Neptune, all of them protected by the same gravitational rhythm. Astronomers, with a certain affection, call these objects the Plutinos, the little Plutos, and they are only one of several great families of objects that make up the layered structure of the belt. So Neptune is not merely a neighbour of the Kuiper Belt sitting innocently beside it. Neptune is its architect. Neptune carved it. The sharp inner edge of the belt, which sits almost exactly at Neptune's own orbital distance, is no coincidence. It is Neptune's signature. The resonant families, the scattered orbits, the separation of the populations, all of it is the lingering record of Neptune's long migration through the dark. And that record tells us something sobering and grand at the same time. It tells us that the solar system did not form gently in tidy fixed rings and then simply hold still. It tells us the solar system went through a violent reorganization in its youth, that the planets moved, interacted, and rearranged the entire structure around them. The Kuiper Belt preserves the scars of that upheaval. Every resonant family, every gap in the orbits, every cluster of objects sharing a similar path is a forensic clue, pointing back across 4 billion years to events no one was there to witness. We will return to that violence later and look at it directly, because it was far more dramatic than the calm word migration suggests. But first, we should meet the families themselves, the distinct populations that share that vast frozen zone, each one carrying its own history, each one a different chapter of the same long story. The Kuiper Belt is not one thing. It is several things, layered together in the same broad region of space, like different strata of rock layered in the wall of a canyon, And just as a geologist can read the history of a landscape in those layers, an astronomer can read the history of the outer solar system in the families of the belt. The first family is the one astronomers call the cold classical belt, and the word cold here does not refer to temperature, because everything out there is unimaginably cold. It refers to the orbits. The cold classical objects move on calm, well-behaved paths, nearly circular, lying close to the flat plane of the solar system, clustered in a band roughly between 42 and 47 astronomical units from the Sun. Their orbits are gentle, they are undisturbed, and that gentleness is itself a piece of evidence. The cold classical objects appear to have escaped the worst of Neptune's violent sculpting. They seem to have formed more or less where we find them today, and to have been left largely in peace ever since. They are, as far as anyone can tell, the least disturbed, most primordial population in the entire solar system, the closest thing that exists to original untouched construction material, still sitting where it was first laid down. When astronomers want to study the solar system as it was at the very beginning, before the Great Rearrangement, the cold classical belt is where they look. We will come back to these quiet objects, because one of them, when a spacecraft finally reached it, revealed something genuinely beautiful. The second family occupies much the same distances, but it behaves very differently. Astronomers call it the hot classical population. Again, not a comment on temperature, but on motion. The hot classical objects move on more tilted, more stretched, more agitated orbits. They are restless where the cold classical objects are calm. And that restlessness tells a story. It strongly suggests that the hot classical objects did not form where we find them. It suggests they were thrown there, scattered into their current paths by gravitational encounters during the chaotic era of Neptune's migration. They are migrants. They carry the agitation of their journey in the shape of their orbits. The third family is the resonant population, the Plutinos and their cousins, the objects caught in Neptune's gravitational rhythms. They are the planet's prisoners in a sense, but well-protected prisoners. Locked into their tidy whole number ratios, they are shielded from disaster, escorted around the Sun in lockstep with the giant that captured them. And then, reaching out beyond all of these, there is the scattered disk. The scattered disk is the wild frontier of the belt, a population of objects on long, dramatically stretched eccentric orbits. A scattered disk object might swing inward to 30 astronomical units, near the inner edge of the belt, and then sweep outward to several hundred astronomical units before turning around and falling back again. These are the objects that Neptune did not capture and did not destroy, but flung, hurled outward into enormous looping paths that carry them far into the dark and bring them back only briefly before sending them out again. The boundary between the scattered disk and the rest of the Kuiper Belt is genuinely debated among astronomers. Some count the scattered disk as part of the broader Kuiper Belt family. Others treat it as a distinct population in its own right. But the physical reality underneath the debate is not in doubt. The Sun's outer realm is not a single simple ring. It is a complex, layered, three-dimensional distribution of icy worlds, shaped over billions of years by gravity, and still carrying, in every orbit, in every family, in every cluster, the fingerprints of how it came to be. Reading those families is like reading the rings of an ancient tree, or the layers in an ice core drilled from a glacier. Each one preserves a different season of the solar system's long youth, and we're only beginning to learn how to read them. There is something almost haunting about how thoroughly the Kuiper Belt has been left out of the human picture of the solar system. It is not a secret. It is not contested. It is not new, and yet it lives in a kind of collective blind spot, acknowledged by science and invisible to almost everyone else. Think again about the diagrams, the classroom poster, the illustration in the children's book, the animation that drifts across a screen. In every one of them, the planets are drawn at roughly even intervals, the distances are squeezed and compressed to fit the page, and the whole thing comes to a tidy stop at Neptune, or perhaps at Pluto. The Kuiper Belt, if it appears at all, appears as a faint dotted arc at the very margin, an afterthought, a footnote, a thin grey suggestion that there might be a little something out there. This is not a trivial omission. It is a quiet, lifelong distortion of reality, and it shapes how billions of people understand the structure of their own home. The distortion does its damage by creating a false sense of completeness. Because the planets have names, and spacecraft have visited them, and beautiful photographs of them exist, the solar system feels finished. It feels mapped. It feels like a story that has already been told, with only minor revisions left to make. People carry, without ever quite examining it, the comfortable belief that we know where we live. But the Kuiper Belt is not finished. It is barely started. Consider the raw arithmetic of our exploration. In the entire history of the human species, exactly one spacecraft has ever travelled to the Kuiper Belt for close-range science. 1. NASA's New Horizons probe, launched in 2006. It swept past Pluto in 2015, and then, in 2019, it passed a single small Kuiper Belt object far beyond Pluto. Those two brief encounters, two fast flybys, each lasting only hours, represent the complete sum of direct human exploration in a region that spans billions upon billions of miles. No orbiter has ever circled a Kuiper Belt object, settling in to study one patiently over months and years. No lander has ever touched the surface of one. No rover has ever rolled across the frozen ground of one. The Kuiper Belt has been visited the way a passenger on a fast train glimpses a distant town through the window, a flash of something, gone before it can be properly seen, and the telescopes that study the belt from afar are working at the very edge of what is possible. A typical Kuiper Belt object 100 kilometers across, viewed from Earth, is something like 10 million times fainter than the dimmest star your unaided eye can see on the darkest night. To find such an object, and then to study it, requires the largest telescopes humanity has built, the longest and most patient exposures, and image processing techniques sophisticated enough to coax a single slow drifting speck out of a field of motionless stars. The surveys are improving, and improving fast. We will come to the great new observatory that is about to transform everything. But even the most optimistic projections make one thing plain. The overwhelming majority of the Kuiper Belt remains unseen. Most of it has never been catalogued, never been photographed, never been counted. It is out there in the dark, exactly as it has been for 4.5 billion years, waiting. So when you hear someone say that we've explored the solar system, hold that statement gently up to the light. We've explored a small, bright, warm core of it, and we've mistaken that core for the whole. The frontier is not a thin borderland at the edge of the known. The frontier is the dominant reality. The wilderness is vastly larger than the settlement, and the wilderness begins right past Neptune. There is a number attached to the Kuiper Belt that almost no one ever mentions, because it is genuinely difficult to think about. It is not the distance. It is not the population. It is the volume, the sheer three-dimensional quantity of space the belt occupies. The Kuiper Belt is not a thin ring, like a hoop laid flat. It is a thick torus, a deep, fat, three-dimensional donut of space, extending well above and well below the flat plane of the solar system, and the amount of space enclosed within it is so large that the ordinary language of comparison begins to fail. Let me try to give you something to hold on to. Think about the volume of space enclosed by the Earth's own orbit around the Sun, the entire vast sphere that contains our planet's yearly journey. That is already an enormous region. It is a sphere 93 million miles in radius. Light itself, crossing from the center of that sphere to its edge, needs a full 8 minutes to make the trip. Picture the totality of it. Every cubic mile of vacuum between us and the Sun, every point of space our world passes through across the turning of a complete year. That is not a small place. That is a place so large that the human mind cannot truly picture it, and quietly substitutes a symbol for it instead. Now take that entire sphere, the whole of it, and understand that it is roughly 100,000th of the volume of the Kuiper Belt. The Kuiper Belt is something like 100,000 times more voluminous than the entire sphere of the Earth's orbit. Take that already incomprehensible region, the sphere that contains our whole year, and multiply it 100,000 times. That is the size of the place we're talking about. The orbital sphere of the Earth vanishes inside the Kuiper Belt the way a single thimble of water vanishes inside the cargo tank of an ocean ship. And here is the part that makes the volume truly disorienting. Despite holding hundreds of thousands, perhaps hundreds of millions of objects, that staggering volume is, almost everywhere, completely empty. The objects of the Kuiper Belt are real, and they are numerous, but they are scattered through such an immensity of space that the distances between them are almost beyond belief. The average gap between two large Kuiper Belt objects is measured in tens of millions of miles. To give that some shape, the distance between Earth and Mars when the two planets are closest together in their orbits is roughly 34 million miles. That distance, the entire span from our world to the red planet, is about the typical gap between one Kuiper Belt object and its nearest large neighbour. Each frozen world drifts alone in its own private expanse of nothing, separated from the next by a void wide enough to swallow the orbit of an inner planet whole. This is a particular kind of emptiness, and it is worth sitting with for a moment, because it is not an emptiness any of us has ever truly experienced. It is not the emptiness of a dark field in the countryside, far from any town. It is not even the emptiness of the space between Mars and Jupiter, where at least the sun still blazes warmly overhead, and the bright planets still hang as recognizable points in the sky. The emptiness of the Kuiper Belt is something more total than that. It is emptiness on a scale that erases context entirely. There are no landmarks. There are no reference points. There is no way standing out there to sense distance or direction at all without instruments. The inner solar system, for all its vastness, gives a being a sense of place. Stand on any inner world, look up, and you see evidence that you belong to a system, a structured family of bright objects sharing a neighborhood, a warm sun anchoring it all. The Kuiper Belt offers no such comfort. Its objects are so far apart that each one exists, in a real and practical sense, in a private universe of empty space, connected to its neighbours only by the invisible mathematics of orbital mechanics, and never by anything you could see, or point to, or reach. It is a wilderness in the oldest and most literal meaning of the word, a place where the very structures that anchor a mind's sense of where it is begin, quietly, to dissolve. And yet, And this is the strange and wonderful turn in the story. The wilderness is not featureless. It is not simply a uniform haze of scattered ice. It contains worlds, real worlds, with surfaces and geology, with moons and histories, with shapes and stories stretching all the way back to the birth of the sun. Some of them are hundreds of kilometers across. A few of them rival small planets. And what we have learned about them in just the last few decades has overturned assumptions that astronomers held with confidence for a very long time. So let us go and meet them. For most of a century, Pluto was treated as a loner, the ninth planet, the runt at the back of the line, the small, cold, distant period at the end of the solar system's sentence. Generations of schoolchildren learned its name in sequence with the others: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and the implication of that sequence was always the same. Pluto was the last one. Beyond Pluto, nothing. The story ended there. That story was never true. And the moment astronomers began to discover what actually surrounds Pluto out in the dark, the entire framing of it collapsed. Pluto is not a loner. Pluto is a local. It is one resident among a vast population of icy bodies, all of them orbiting in the same broad outer zone. It is the most famous member of the Kuiper Belt, famous because it was found first, 80 years before the rest of its family. But it is not the only one, and it is not even the most massive. Pluto is embedded in a community of frozen worlds that stretches across billions of miles of space, and the variety within that community is one of the most underappreciated facts in all of modern planetary science. Let us begin with Pluto itself, properly this time, not as a lonely outpost but as one world among many. Pluto has a diameter of roughly 2,370 kilometers. It is in fact smaller than our own moon. Its surface is an intricate patchwork of nitrogen ice, methane frost and carbon monoxide ice, sculpted by processes that scientists are still working to fully understand. And Pluto does not orbit alone in the small sense either. It has 5 known moons. The largest of them, Charon, is so enormous relative to Pluto itself that the two of them do not really orbit in the way a planet and a moon usually do. Instead, they orbit a shared centre of gravity that lies in the empty space between them. They circle each other. The Pluto-Charon system is sometimes described not as a planet and its moon, but as a binary world, a true gravitational partnership, unique among everything we know in the solar system. We will return to Charon later, because when a spacecraft finally reached it, Charon had revelations of its own. But Pluto is far from the only sizable world in the Kuiper Belt. There is a small set of objects out there large enough and round enough to be called dwarf planets in their own right, and each of them is a world worth knowing. The first of them, after Pluto, is Eris. Eris was discovered in 2005, and its discovery is the reason, the direct specific reason, that Pluto is no longer called the 9th planet. Eris has a diameter of about 2,326 kilometers. That is almost exactly the size of Pluto, and in mass, Eris is actually slightly heavier than Pluto. When astronomers found Eris, they were faced with a genuinely simple and genuinely awkward question. If Pluto is a planet, then Eris, being just as large and even more massive, must also be a planet. So either the solar system suddenly had a 10th planet, and very likely many more waiting to be found, or the definition of the word planet needed to change. In 2006, the International Astronomical Union chose to change the definition. They created a new category, the dwarf planet, and they placed both Pluto and Eris within it. Pluto did not shrink, and it did not move, and it did not become any less interesting on that day. It simply received a more accurate description of what it had always been. Not a lonely ninth world, but one of the grandest members of a vast and crowded family. Eris orbits much farther out than Pluto, on a long and stretched path. At its closest approach to the Sun, it comes into about 38 astronomical units. At its farthest, it swings out to nearly 98, deep into the scattered disk. Its surface is wrapped in a brilliant frost of frozen nitrogen and methane, which makes it one of the most reflective bodies in the entire solar system. A small, dazzlingly bright world adrift in the dark. And Eris has a moon of its own, named Dysnomia, roughly 600 kilometers across. Then there is Makemake, also discovered in 2005. Makemake orbits at an average distance of about 46 astronomical units and is roughly 1,430 kilometers across. Its surface is dominated by frozen methane and ethane, and there are signs that the methane ice exists there in large crystalline grains, a clue suggesting a surface that has been slowly worked and processed over immense stretches of time by the faint ultraviolet light of the distant Sun. In 2015, the Hubble Space Telescope detected a small dark moon orbiting Makemake, a faint companion to a faint world. And then there is Haumea, which may be the strangest large object in the entire solar system. Haumea is not round. Almost every sizable world you can name is round, because gravity, given enough mass, pulls a body inexorably toward a sphere. Haumea defies this. Measured along its longest axis, it is about 2,320 kilometers across. But it is not a ball. It is shaped like an egg, or perhaps more precisely like a flattened, stretched-out rugby ball. The reason is its spin. Haumea rotates astonishingly fast, completing one full turn in under 4 hours. That ferocious rotation generates so much outward force that it has physically stretched the world, pulling it out of a round into its strange elongated shape. Astronomers believe that this extreme spin is the leftover signature of a colossal ancient collision, an impact so violent that it set Haumea whirling and also flung off a family of smaller icy fragments that still share similar orbits today. It is the only known collisional family in the entire Kuiper Belt. Haumea also has 2 moons of its own, named Hi'iaka and Namaka. And in 2017, astronomers discovered that Haumea possesses something no one expected. A ring. A delicate ring of material encircling it. The first ring ever found around an object beyond Neptune. That discovery of a ring around Haumea was startling enough on its own, but it was not the last of its kind. Consider Quaoar, a Kuiper Belt object orbiting at about 43 astronomical units, with a diameter of roughly 1,100 kilometers. Quaoar is smaller than the largest dwarf planets, but it became, in 2022, the center of one of the most genuinely puzzling discoveries in recent outer solar system science. Using a technique called stellar occultation, watching the flicker of a distant star's light as Quaoar passes in front of it, astronomers detected a ring around Quaoar as well. What made this ring so strange was where it sat. There is a boundary around any world called the Roche limit. Inside that boundary, the tidal forces from the world are strong enough to prevent loose material from clumping together. Outside it, material should gather and coalesce into a moon. Quaoar's ring sits well outside its Roche limit, in the zone where, according to every established model, the ring material should long ago have pulled itself together into a small moon. And yet there it is, still a ring. The discovery genuinely unsettled the theorists, and explaining how that ring can exist where it does remains an open and active question. And in 2025, astronomers reported evidence that Kuiper may have an additional moon as well, making this distant, modest-sounding world a more intricate little system than anyone had imagined. Pluto, Eris, Makemake, Haumea, Kuiper. 5 worlds, each one strange, each one a place, and these 5 are merely the most prominent members of a far larger crowd. Out beyond Neptune there are hundreds of other Kuiper Belt objects larger than 200 kilometers across. Many of them have moons. Some of them surely have complex and varied surfaces we have never resolved. And a few of the very largest may even hold, somewhere deep beneath their frozen shells, thin hidden layers of liquid, kept from freezing by the faint warmth of radioactive decay in their rocky cores. Stop and weigh what this means against the inner solar system you grew up picturing. The familiar inner system, from Mercury out to Neptune, contains 8 major planets, a scattering of dwarf planets, and a few 100,000 asteroids. The Kuiper Belt, by contrast, contains multiple dwarf planets, very likely hundreds of thousands of objects larger than 100 kilometers, and billions of smaller bodies. By the simple measure of how many individual worlds it contains, the outer solar system overwhelms the inner one completely. The region almost everyone ignores holds far more worlds than the region almost everyone studies. But knowing how many worlds are out there is only half the wonder. The other half is the question of how they came to be where they are, and the answer to that question is a story of remarkable violence. The objects of the Kuiper Belt did not drift into their orbits at random. They were placed there, placed by a sequence of events that tore through the early solar system and reshaped its entire architecture during its first few 100 million years. The leading explanation for that reshaping is a framework that astronomers usually call the Nice model, named for the city in France where it was developed. And the picture it paints of the young solar system is not one of calm and order, it is one of chaos. The Nice model proposes that the 4 giant planets first formed in a much more compact arrangement, closer together and closer to the Sun than they sit today. Surrounding them, stretching outward, was a massive disk of leftover icy planetesimals. The unused building blocks, dense and thick, an enormous reservoir of frozen debris. For a long while this arrangement held, and then, slowly, the gravitational conversation between the planets and that great disk of debris pushed the whole system past a tipping point. The compact arrangement of the giants became unstable, and the solar system fell into a period of chaotic, large-scale migration. It did not happen in an instant. It unfolded across tens of millions of years. But during that long upheaval, Neptune moved dramatically outward, grinding its way through the primordial disk like a slow and unstoppable plough pushing through a field. And as Neptune advanced, it threw the disk into disarray. Picture a hand sweeping slowly but irresistibly across a table covered in marbles. Some marbles are knocked forward, some are knocked aside, some are sent flying off the edge entirely. Neptune did all of this, to trillions of icy bodies, across tens of millions of years. Vast numbers of objects were flung clean out of the solar system, hurled onto escape paths that carried them out into interstellar space, lost forever, never to return. Others were thrown inward, raining down toward the Sun and the inner planets. This inward rain was so intense that it has a name, a period of heavy bombardment. The icy bodies that fell inward struck the young inner worlds again and again. Many of the ancient craters and great impact basins we still see today, the battered face of the moon, the old scars on Mercury and Mars, may date from this very era, when the outer solar system's debris came pouring down. Still other objects were not ejected and not thrown inward, but captured, locked by Neptune's gravity into the resonances we spoke of earlier, preserved in stable rhythms that have held for billions of years since. The scale of the disruption is difficult to overstate. The primordial disk that existed before Neptune's migration was far more massive than the Kuiper Belt we see today. What we observe now is only a remnant, a small surviving fraction, perhaps just a few % of the original population. The rest was scattered, ejected, consumed, or hurled into the sun. The modern Kuiper Belt is not the original disk at all. It is the debris field left behind after the original disk was torn apart. And this gives the Kuiper Belt a peculiar, almost paradoxical character. It is, at the same time, ancient and young. Its objects are ancient, their material condensed from the solar nebula 4.5 billion years ago, and has changed little since. But their orbits, their addresses, their arrangement in space are younger, imposed upon them by Neptune's migration during the chaos that came afterward. The objects are old, their positions are newer. The bodies themselves are original construction material. The layout of the neighbourhood was drawn up later, in fire and gravity. That is why the families of the belt matter so much. The cold, classical objects, calm and undisturbed, preserve the conditions of the very beginning. The hot, classical and scattered objects, restless and stretched, record the violence of the migration. Reading the populations of the Kuiper Belt is, quite literally, reading the autobiography of the solar system, a book written not in words but in orbits, and only now being slowly, carefully translated. And the most precious page in that book, the one that preserves the gentlest and oldest handwriting, is the cold classical belt, which is exactly where a small spacecraft, in the first hours of a new year, went to read it. In 2019, on the first day of January, the New Horizons spacecraft did something no machine and no human being had ever done before. It flew past a small, ancient object of the cold classical belt, a body called Arrokoth, and it sent back the first close portrait of one of the most primordial, least disturbed objects in the entire solar system. We will follow New Horizons' whole long journey later, properly, from its launch to its lonely present. But the shape of Arrokoth belongs here, in the story of how the worlds of the belt came to be, because that shape answered a question. Arrokoth orbits in the cold classical belt at roughly 44 astronomical units from the Sun. It is small, only about 36 kilometers from end to end. And when the images came back, they showed something that looked, immediately and unmistakably, like a snowman. Arrokoth is made of two roughly rounded lobes, a larger one and a smaller one, joined together at a narrow neck. Two frozen spheres gently fused. That shape is called a contact binary, and Arrokoth was the first one ever seen up close anywhere. The larger lobe is about 22 kilometers across, the smaller about 14. Both lobes are remarkably smooth, marked by very few craters, a surface that has plainly been left undisturbed for an enormous span of time. And the colour is a uniform, gentle red, the colour of organic rich ices that have been slowly worked over billions of years by cosmic rays and the faint ultraviolet light of the distant sun. But the shape was the revelation, because the shape told scientists with quiet certainty how Arrokoth was made. Arrokoth was not built by violence. The two lobes did not collide and smash together. The smoothness, the gentle joining, the survival of both lobes as recognizable rounded shapes, all of it pointed to the opposite of a collision. The two lobes came together slowly. They drifted into contact at a speed of only a few meters per second, slow enough that a person could comfortably jog faster. They did not crash. They touched. They settled against each other and stayed. This gentle merger is exactly what a particular theory of planet formation predicts. The theory is called the streaming instability. It proposes that the small solid grains in the young solar nebula did not have to build up planets one slow, lucky, sticking collision at a time. Instead, aerodynamic interactions with the surrounding gas could gather the grains into dense filaments, concentrated clouds of pebble-sized material. And when such a cloud grew dense enough, it could collapse directly under its own gravity, gently, into a bound object. Such a collapsing cloud would naturally tend to split into two clumps, which would orbit one another, slowly lose energy, and finally spiral together into a gentle touching pair, into exactly the snowman shape that Arrokoth wears. So Arrokoth is not just an object. It is a piece of evidence, 4.5 billion years old, frozen and preserved and finally photographed. It tells us that the building blocks of the outer solar system formed quietly, by gravitational collapse, rather than by a long, violent series of crashes, and Arrokoth is not a freak. Observations from Earth, careful studies of how the brightness of distant Kuiper Belt objects rises and falls as they rotate, suggest that contact binaries are common out there. By some estimates, somewhere between 10 and 30% of the small objects in the Kuiper Belt may wear that same gentle two-lobed shape. The frozen frontier, it turns out, is scattered with snowmen, each one a sculpture left over from the moment of creation, kept in a deep freeze so perfect that nothing has touched it since. In early 2026, a study published in a leading astronomy journal carried this understanding further. A researcher named Jackson Barnes, working at Michigan State University, used detailed computer simulations to model the process directly, to watch, in a virtual nebula, a slowly spinning cloud of pebble-sized material collapse, split into two gravitationally bound lobes, and then bring those lobes gently together without shattering either one. The simulations produced a whole variety of two-lobed shapes, with different lobe sizes and proportions, matching the variety actually observed in the belt. The work strengthened the case considerably. Objects like Arrokoth are most likely born as two-lobed bodies from the very start, rather than being assembled later by a fortunate slow-motion collision. And there is a further thread. The streaming instability does not only predict pairs, it predicts that gravitational collapse should sometimes produce triples, 3-bound bodies instead of 2. In early 2025, observations from the Hubble Space Telescope examined a Kuiper Belt system that had been catalogued as a binary and found orbital behavior suggesting a hidden third member, too close to its companion to be separated in the images. If that finding holds, it would be only the second triple system ever identified in the Kuiper Belt, and it would quietly confirm a prediction and hint that many more hidden triples are waiting out there for sharper instruments to reveal. Every one of these discoveries does the same quiet, profound thing. It transforms the Kuiper Belt from a passive heap of leftover rubble into an active, readable record of how planets are born. Every contact binary is a data point. Every binary orbit encodes the conditions of the cloud that collapsed to make it. Every surface records the chemistry of the disk at that exact distance from the young sun. The Kuiper Belt is not a junkyard. It is an archive, and we have only just begun to read it. There is a way in which the Kuiper Belt, for all its remoteness, reaches in and touches the inner solar system, touches it gently, regularly and visibly. It does so through comets. You have almost certainly seen a comet, or at least a picture of one, a glowing head trailing a long, soft tail across the sky, one of the oldest and most striking sights in all of human experience. Comets have been recorded, feared, and wondered at for thousands of years, and a particular family of them, the short-period comets, the ones that loop back into the sun's vicinity on cycles of roughly 20 years or less, come for the most part directly from the Kuiper Belt. You may know some of their names without realizing where they were born. Comet Tempel 1, visited by NASA's Deep Impact mission. Comet 67P, the one whose full name is Churyumov-Gerasimenko, which the European Space Agency's Rosetta spacecraft did not merely fly past but actually orbited and studied, even setting a small lander upon its surface. Dozens of these short-period comets follow orbits that trace clearly back to a Kuiper Belt origin. They are pieces of the frozen frontier gone wandering toward the fire, the journey that turns a quiet Kuiper Belt object into a blazing comet is a slow and rather beautiful one, and it is worth following. It begins with a nudge. Out near the inner edge of the belt, Neptune's gravity occasionally destabilizes an icy body, tipping it onto a new orbit that crosses Neptune's path. From there, a long series of gravitational encounters with the giant planets can gradually rework the object's orbit, pulling the closest point of its approach to the sun steadily inward over millions of years. It is like a slow conveyor belt, carrying frozen bodies, one at a time, out of the deep cold and toward the warmth. For most of that journey, nothing happens. The object simply drifts, as it has drifted for 4.5 billion years, its surface locked near 230 degrees below zero, its volatile ices sealed safely beneath a dark crust. But somewhere around 5 to 10 astronomical units from the Sun, roughly the distances of Jupiter and Saturn, the slowly accumulating warmth finally becomes enough to matter. The most volatile ices begin to respond. Carbon monoxide stirs first, then carbon dioxide. Molecules that have been frozen solid since before the Earth existed begin, for the first time, to move, passing directly from solid ice to gas without ever becoming liquid. As the object crosses inside the orbit of Jupiter, the transformation accelerates dramatically. The sun's light, now hundreds of times stronger than anything the object ever felt in the Kuiper Belt, drives heat down through the dark crust and into the volatile ices below. Gas erupts through cracks and vents, carrying dust with it, spraying outward into the vacuum in jets. The object grows a coma, a soft, glowing cloud of gas and dust wrapped around its small frozen heart. And as it presses closer still, the pressure of sunlight and the stream of the solar wind push that material outward into long streaming tails, one of ionized gas, pointing straight away from the sun, and one of dust, curving gently along the path of the orbit. The comet has woken up. After 4.5 billion years of perfect frozen stillness, it is being slowly taken apart by the very star that created it. This means that every comet you have ever seen, or ever will see, is a messenger from the deep cold. It carries material that has been kept near absolute stillness for the entire history of the solar system. Material that still holds, unchanged, the chemical fingerprint of the era of creation. When a comet's tail unfurls across the night sky, you're watching ancient Kuiper Belt ice turn to vapor in real time, releasing molecules that were assembled before the Earth had a surface to stand on. And there is one more thread to this, a thread that reaches all the way to us. During that great era of heavy bombardment, when Neptune's migration was raining icy bodies down upon the inner solar system, a portion of that frozen material fell upon the young Earth. Some scientists believe that a meaningful fraction of the water in our oceans may have been delivered, at least in part, by impacts of icy bodies during that distant age. The evidence is genuinely debated. The chemical signatures are complicated, and water-rich asteroids almost certainly contributed as well, and no honest account would claim the question is settled. But the larger point stands firmly, regardless of the details. The Kuiper Belt is not an isolated, disconnected region with no bearing on our lives. It is a reservoir that has been quietly feeding material into the inner solar system for billions of years. The frozen frontier and the warm world where you're lying tonight are not strangers, they are kin. If you could somehow line up the worlds of the Kuiper Belt and look at them, one after another, you would notice something. They are not all the same colour. The largest objects, Pluto, Eris, Make, were surfaces dominated by the bright volatile ices, frozen methane, nitrogen, and carbon monoxide. These ices are light enough and active enough that they can evaporate and redeposit over the long seasonal cycles of these worlds, slowly resurfacing them, giving them a brightness and a freshness that genuinely surprised astronomers when they were measured. Pluto's nitrogen ice flows like a glacier under its own weight, though at a pace measured in centimetres per century. Eris is so brilliantly reflective that it is among the brightest objects in the whole solar system, possibly because nitrogen frost keeps condensing fresh and clean onto its surface as it travels through the coldest part of its long orbit. The smaller objects tell a different chromatic story. Their surfaces tend to be dominated by water ice, but water ice mixed with something darker, something reddish, a class of compounds called tholins. Tholins are one of the quietly remarkable things in the outer solar system. They form when simple molecules, methane, nitrogen and the like, are bombarded over millions and millions of years by ultraviolet light and cosmic rays. That slow, patient irradiation breaks the simple molecules apart and recombines them into a complex tarry residue, rich in carbon and stained a distinctive brick-red colour. Many Kuiper Belt objects look red, or even deeply ultra-red in the telescope, and tholins are the leading explanation. And here is what makes tholins genuinely fascinating, almost philosophically so. They are a form of complex carbon-based chemistry, assembled with no biology involved whatsoever. They are intricate organic molecules built by nothing more than radiation, acting upon simple ices across cosmic stretches of time. The Kuiper Belt is, in a real sense, running a slow chemistry experiment on every surface it holds, and has been running it since before life began on Earth. The colours are not random, and that is the clue scientists treasure most. The calm, undisturbed, cold classical objects tend to be redder. The agitated, hot classical and scattered objects tend to be greyer, more neutral. And that divide lines up with history. The red objects formed in place, out in the deep cold, and were never heated or stirred. The greyer objects were scattered out from regions closer to the sun, where it was warmer, and that warmth may have altered their surface chemistry before they were ever flung outward. Colour, in the Kuiper Belt, is a tracer of origin. The hue of a frozen world is a quiet record of where it was born and what happened to it. Some objects refuse to fit any tidy category at all. In 2018, astronomers studying one particular Kuiper Belt object found that its surface chemistry resembled, of all things, the carbon-rich asteroids of the inner solar system, bearing signs of ferric oxides and clay-like phyllosilicate minerals utterly unlike anything else seen beyond Neptune. If that interpretation holds, then that object may have formed much closer to the Sun, and then been hurled all the way out into the frozen dark during the Great Migration. It would be a piece of the warm inner solar system stranded in the cold, an exile, a traveller from a hotter past, drifting now among worlds that were never anything but ice. All of this complicates any simple story you might want to tell about the Kuiper Belt. It is not a uniform field of identical dirty snowballs. It is a mixed and varied community, objects of different origins, different histories, different surfaces, different inner structures. Some are probably solid mixtures of rock and ice. Some are likely loose rubble piles, held together gently by their own faint gravity, and a few of the largest may be genuinely differentiated, with rocky cores and icy mantles, and perhaps, thin hidden layers of liquid water, or water mixed with ammonia, kept from freezing by the last faint warmth of radioactive decay. That last possibility leads to one of the most quietly astonishing questions anyone can ask about the Kuiper Belt. It is a question that 30 years ago would have sounded absurd, and today is asked seriously by serious people. Could any of these frozen, distant, sunless worlds hold conditions suitable for the chemistry that precedes life, or even, in some buried and improbable place, for life itself? The question is not as foolish as the cold and the distance make it sound. We have learned, in recent decades, that the moons Europa and Enceladus, also far from the Sun, also frozen on the outside, almost certainly hold oceans of liquid water beneath their icy shells, kept warm not by sunlight, but by the flexing of tides. That discovery widened the very definition of where life might be possible, and so the reasoning extends cautiously outward. If a large Kuiper Belt object held enough internal heat to keep a thin layer of liquid beneath its ice, and if that liquid touched a rocky core that could feed it chemical energy, then the bare theoretical conditions for life would, however faintly, be met. There is no evidence, none, that life exists anywhere in the Kuiper Belt. The idea is entirely speculative, and it should be held lightly. But the simple fact that it can be discussed seriously at all is itself a measure of how far our understanding has come. 30 years ago, the objects beyond Neptune were assumed to be inert, dead chunks of dirty ice. Today they are understood as complex, varied, scientifically rich worlds, with geology, with organic chemistry, and possibly, just possibly, with hidden liquid interiors. The dead zone was never dead. We simply could not see it well enough to know. There is one more mystery hidden in the Kuiper Belt, and it is the kind of mystery that has the power to add an entire new world to the solar system. For years, astronomers have noticed something peculiar about a small set of the most distant Kuiper Belt objects, bodies on long, stretched, eccentric orbits, far out beyond the main belt. These particular objects appear to share an unusual alignment. Their orbits seem to cluster, to point in similar directions, to lean the same way, far more than random chance should allow. When a pattern like that appears in nature, it demands an explanation. And one possible explanation is gravity. Specifically, the gravity of something large and unseen. This is the origin of one of the most intriguing ideas in modern astronomy. The hypothesis of an undiscovered planet, sometimes called Planet 9, orbiting far beyond everything we have catalogued, hundreds of astronomical units from the Sun, a world large enough that its gentle, distant gravitational influence could be shepherding those far-flung Kuiper Belt objects into their strange shared alignment. In September of 2025, a survey analysis published in a respected astronomy journal added a new thread to the search. Examining a fresh data set and the orbital clustering within it, the study proposed that an unseen planet, one at least 25 times more massive than Pluto, might reside within the broad Kuiper Belt region itself. But it is important to be honest and careful here, because this is genuinely unresolved science, and honesty is more interesting than certainty. The hypothetical planet has not been found. No telescope on the ground or in space has yet captured a direct image of it, and not every astronomer believes it is there at all. Some argue, with real force, that the orbital clustering is not a real physical pattern, but a statistical illusion, an artifact created by the simple fact that our surveys have searched some parts of the sky more thoroughly than others, and so have found objects in some directions more easily than in others. Others maintain just as firmly that the clustering is real, and that a real cause is required to explain it. The debate is vigorous, it is unsettled, and it is unlikely to be resolved by argument. It will be resolved by data, by a more complete, less biased census of the outer solar system. And that census is coming. Whether or not Planet 9 turns out to exist, the hypothesis illustrates something true and important about the Kuiper Belt as a whole. This region still holds fundamental surprises. Its population is incompletely catalogued. Its structure is only partly understood. Its largest members may not even have been discovered yet. The Kuiper Belt is not a solved problem, filed neatly away in the back of a textbook. It is a living frontier, a place where genuinely major revisions to our understanding of the solar system remain entirely possible. There may, right now, tonight, be a world out there larger than the Earth, orbiting our own sun that no human eye has ever seen. For all the telescopes, all the surveys, all the careful mathematics, there is only one way to truly know a distant world: to go there. And only once has anything we built ever gone to the Kuiper Belt. So let us follow it. The entire journey, from the launch pad to the lonely dark where it drifts tonight. The spacecraft is called New Horizons. It is not large. It is roughly the size and weight of a baby grand piano, and it carries a modest suite of 7 scientific instruments: cameras, spectrometers, a dust counter, a plasma detector. It was launched from Earth on the 19th of January 2006 atop a powerful rocket, and it left our planet faster than any spacecraft before it had ever left. The numbers from those first hours are worth savouring, because they put everything that follows into proportion. New Horizons crossed the orbit of the Moon, a distance that took the Apollo astronauts roughly 3 days to cover, in just 9 hours. It passed the orbit of Mars in less than 3 months. It reached giant Jupiter in just 13 months, and there it performed a gravitational slingshot, swinging close past the giant planet and stealing a little of its orbital energy. flinging itself onward toward the outer solar system faster still. And then it began the long part of the journey, the part measured not in months but in years. Because even at its tremendous speed, even moving faster than any object humans had ever launched, the gulf to Pluto was so vast that New Horizons would need 9.5 years of continuous flight to cross it. 9.5 years. A child born on the day of that launch would be most of the way through elementary school by the time the spacecraft arrived. New Horizons crossed 3 billion miles of empty space, and for almost all of that time there was nothing to do but coast and sleep and wait and hold its course through the dark. It arrived on the 14th of July 2015, and it arrived fast. New Horizons swept toward Pluto at roughly 14 kilometers every second, so fast that slowing down to enter orbit was simply impossible. There was never any question of orbiting Pluto. The entire encounter would be a single flyby, one high-speed pass during which every instrument aboard would fire continuously, gathering as much data as it possibly could in the few precious hours that Pluto filled its view. The closest approach carried the spacecraft to within about 12,500 kilometers of Pluto's surface, and then there was the wait. Because of the immense distance, even travelling at the speed of light, the signal confirming that New Horizons had survived its flyby and gathered its data needed 4 hours and 25 minutes to cross the solar system and reach the mission team waiting on Earth. The spacecraft completed its encounter, and then everyone simply had to wait for 4.5 hours to learn whether it had worked at all. It had worked. And what came back across that vast distance slowly, over the following months, did not merely add detail to our knowledge of Pluto, it rewrote it. Before New Horizons arrived, almost everyone expected Pluto to be boring. That is a blunt way to say it, but it is honest. The expectation, grounded in decades of theory, was that Pluto would be a frozen relic, an ancient, battered, cratered ball of ice, geologically dead for billions of years. The reasoning seemed airtight. Pluto is small. Pluto is unimaginably cold. Pluto is desperately far from the sun, the only obvious source of energy. A world like that has no engine. It has no way to do anything. It should, by every reasonable expectation, be an inert sphere of ice, its surface uniformly scarred by 4.5 billion years of impacts, a dead thing that had not changed since shortly after it formed. The first sharp images came back, and that expectation simply collapsed. What New Horizons revealed was a world of staggering geological richness, a world that was not dead at all, but visibly, demonstrably alive in the geological sense, still shaping itself, still changing. The most famous feature is the Great Pale Shape across one hemisphere, a vast bright region in the unmistakable form of a heart. It is now officially named Tombor Regio, in honour of Clyde Tombaugh, the astronomer who discovered Pluto in 1930. And the left lobe of that heart holds the feature that astonished scientists most of all, an enormous plain of nitrogen ice called Sputnik Planitia, a basin roughly 1,000 kilometres across and several kilometres deep. What made Sputnik Planitia so shocking was what it lacked. It had no craters, none that could be seen. It was one of the smoothest, cleanest surfaces ever observed anywhere in the solar system. And in a region of space where being slowly peppered with impact craters is the normal, expected fate of every surface across billions of years, a blank slate that large can mean only one thing. The surface is young. Something has erased the craters. Something is still happening there, and something is. Scientists studying Sputnik Planitia realize that its nitrogen ice is not static and frozen still. It moves, it churns. The surface of the basin is divided into a pattern of irregular polygonal cells, each one perhaps 30 or 40 kilometers across, separated by shallow troughs. Those cells are the surface signature of convection, slow, ponderous overturn in the nitrogen ice below. Warmer ice rises slowly from the depths of the basin, spreads gently across the surface, cools, and sinks again at the edges. It is the same motion you can see in a pot of thick liquid heated gently on a stove, except here it unfolds across cells the size of cities, on a frozen world 4 billion miles from the sun, completing a single overturn perhaps once every 500,000 years. Slow by any human measure. But geologically that is a vigorous living process on a world that was supposed to be a corpse, and Sputnik Planitia was only the beginning. Around its edges mountain ranges rise abruptly from the basin floor, reaching heights of 3 to 4 kilometers. They are not mountains of rock. They are mountains of water ice. Because at Pluto's brutal temperatures, water ice is no longer soft and yielding. It behaves mechanically like stone. It is hard. It is rigid. It can hold up steep slopes and sharp peaks. Those mountains are blocks of water ice bedrock, standing like frozen sentinels along the shore of a glacial plain of nitrogen. Elsewhere on Pluto, New Horizons found still more variety. Dark reddish patches near the equator stained with tholins, strange blade-like ridges of methane ice, formations called penitentes, standing in vast fields, their sharp edges carved by patterns of sublimation. Impact craters of many sizes did exist outside the young basin, but even many of those showed signs of modification, partly filled with ice, softened, or cut through by fractures. And those fractures are among the most telling things New Horizons saw. Long extensional faults stretch across Pluto's surface, some running for hundreds of kilometers, great cracks where the world's outer shell has been pulled apart. And one explanation for those cracks reaches deep, all the way into Pluto's hidden interior. If Pluto holds beneath its frozen crust a layer of liquid water, an ocean trapped between the rocky core and the ice shell, then the slow freezing of that ocean over geological time would explain the cracks perfectly. Water expands as it freezes. As a subsurface ocean gradually solidifies from the outside in, the expanding ice pushes outward against the shell above it, stretching it, tearing it, opening exactly the kind of long tensional fractures that New Horizons mapped. The possibility that Pluto holds, or once held, a subsurface ocean was one of the most profound results of the entire mission. Thermal models built after the flyby suggest that a layer of liquid water, perhaps mixed with ammonia, which works as a natural antifreeze, could plausibly survive beneath Pluto's ice shell even today. The heat to maintain it would come from the slow radioactive decay of elements in Pluto's rocky core, a faint warmth, but a steady one, insulated from the minus 230-degree surface by kilometers of frozen nitrogen and water ice above. If such an ocean is truly there, then Pluto joins a quietly growing list of solar system worlds, Europa, Enceladus, Titan, Ganymede, where liquid water may persist in hidden darkness, far from any warmth of the sun. And there was the atmosphere. Pluto has one, thin but real and measurable. It is composed mostly of nitrogen, with traces of methane and carbon monoxide. The pressure at the surface is something like 100,000 times lower than Earth's. By any standard we would use on our own world, it is barely more than a vacuum. but that wispy envelope of gas reaches surprisingly high, hundreds of kilometers above the surface. And when New Horizons looked back at Pluto after closest approach, with the sun behind it, the atmosphere lit up in delicate, distinct layers of haze, stacked one above another like the strata of a quiet sky. Those hazes are made of tiny tholin particles, forming high in the atmosphere as ultraviolet sunlight breaks methane molecules apart and sets off a slow cascade of chemistry that builds steadily more complex organic compounds. The particles drift gently downward over time and settle onto the surface, deepening the dark reddish stains on the ground below. And Pluto's atmosphere is not even constant. As Pluto travels along its long 248-year orbit, its distance from the Sun changes significantly, and the atmosphere responds. Surface ices evaporate into gas in the warmer stretches and freeze back onto the ground in the colder ones. The whole atmosphere inflates and deflates over centuries, rising and settling like a single, impossibly slow breath. Every one of these discoveries struck at the same old assumption, the assumption that the Kuiper Belt should be geologically dead. Pluto, a world barely larger than some moons, turns out to sustain churning convective ice, towering mountains, tectonic fractures, a layered hazy atmosphere, and very possibly a hidden ocean. And it does all of this at 40 astronomical units from the Sun, in conditions that, on paper, should permit none of it. And if Pluto can do this, then the implications ripple outward across the whole belt. Dozens of other Kuiper Belt objects are comparable in size. If even a fraction of them are anything like Pluto, the outer solar system may hold a far richer inventory of activity and of hidden liquid water than anyone dared imagine before that small piano-sized spacecraft arrived. While New Horizons was studying Pluto, it was also studying Pluto's great companion, and Charon turned out to be every bit as surprising as Pluto itself. Charon is large. Its diameter is roughly 1,200 kilometers, more than half the diameter of Pluto. That ratio is what makes the pair so unusual. Charon is not a small moon circling a dominant planet. Charon is more like a twin. The two bodies are tidally locked to one another so completely that each forever shows the same single face to the other, the way two dancers might hold each other's gaze and turn together, never looking away. They orbit their shared center of gravity once every 6.5 days, separated by roughly 19,600 kilometers of empty space. No other planet and moon system we know of behaves quite like this. Two worlds locked in a permanent mutual embrace. But where Pluto's surface is bright and active and ever-changing, Charon's tells a quieter, older story. Charon is dominated by water ice, which at these temperatures is stable and inert. It does not evaporate and redeposit the way Pluto's volatile nitrogen and methane do. So Charon has no bright shifting frosts. Instead, it presents a muted landscape of greys and browns, older, more heavily cratered, far less resurfaced than the youthful plains of its partner. Yet Charon is anything but featureless. Its north pole is capped by a strange, dark, reddish stain, a feature given the informal name Mordor Macula. And the leading explanation for that dark cap is one of the most quietly wonderful processes in the solar system, because it connects the two worlds directly across the void between them. It works like this. Methane gas escapes slowly and continuously from Pluto's thin atmosphere. Some of that escaping methane drifts across the gap of space toward Charon. When it reaches Charon's polar regions, it is cold-trapped, frozen down onto the surface during the long, decades-long polar winter, when that pole is turned away from even the faint distant sun. Then, when the pole eventually rotates back into the feeble sunlight, ultraviolet radiation works upon that trapped methane, processing it, over time, into reddish tholins. Across millions of years, this cycle paints a steadily darkening cap of organic material onto Charon's poles. It is atmospheric chemistry conducted across open space, between two separate worlds. One world breathing out, the other slowly catching that breath and turning it into a stain. There is no other process quite like it anywhere we have looked, and Charon's midsection holds something even more dramatic. A vast canyon system stretches across its equator, running for well over 1,000 kilometers and plunging in places to depths of as much as 9 kilometers. To feel that properly, compare it to the Grand Canyon on Earth, which reaches a maximum depth of roughly 1.5 kilometers. Charon's Great Rift is something like 5 times deeper than the Grand Canyon, and it is carved across a world only about 1/10 the diameter of Earth. It is an enormous wound in a small world, and it points, like Pluto's fractures, to a hidden ocean in the past. The most likely explanation is the same one offered for Pluto's cracks. If Charon once held a subsurface ocean of liquid water, then the gradual freezing of that ocean would have expanded the world's interior, stretching the crust above until it tore open along the equator. The Great Canyon would be the scar of that ancient expansion, the lasting mark of internal activity on a world that conventional expectation said should have been silent and still from the day it was born. So both Pluto and Charon may once have cradled liquid water in their depths. Neither is large. Both orbit in a region so cold that the air itself would freeze to the ground. The sun delivers them so little energy that it cannot meaningfully warm anything at all. And yet the evidence points, again and again, to internal warmth, to the slow, patient heat of radioactive decay, quietly sufficient, deep inside small frozen worlds, to keep liquid water from freezing for billions of years. If that can happen at Pluto and Charon, then the question is no longer whether the Kuiper Belt is interesting. The question is how much more it is hiding. There is one more thing worth understanding about Pluto before we leave it behind, and it has to do with time, with the strange stretched out way that time itself unfolds on a world so far from the sun. On Earth, a year is a familiar thing. It is one trip around the sun, 365 days, a cycle short enough that every human being experiences it many times over. We are built to understand a year. We feel its seasons turn. We watch the same year come around again and again, and we measure our whole lives in counts of it. Pluto does not have a year like that. Pluto's year is 248 Earth years long. Sit with that for a moment, here in the quiet. A single orbit of Pluto around the Sun takes 248 of our years to complete. That means no human being has ever lived to see a full Pluto year pass. It means that since Pluto was discovered, back in 1930, it has not yet completed even half of one orbit. The Pluto that astronomers found nearly a century ago has been moving, slowly and steadily, along its enormous path ever since, and it still has not come close to returning to where it was when we first saw it. Every person who was alive on the day Pluto was discovered, and every person born since, will live their entire life within a single fraction of one Plutonian year. And that long, slow year is not a smooth circle. Pluto's orbit is noticeably stretched, an ellipse rather than a ring. At its closest approach to the Sun, Pluto comes inward to about 30 astronomical units. close enough that, for a stretch of its orbit, it actually travels nearer to the Sun than Neptune does. At its farthest, it swings out to about 49 astronomical units, deep into the cold. So across its long year, Pluto's distance from the Sun changes dramatically, and with it, ever so slightly, the faint warmth that distant point of light can offer. This gives Pluto seasons, but seasons unlike anything we could recognize. They do not last for months, they last for decades. A single season on Pluto stretches across more than a human lifetime. A child born at the start of one Plutonian season could grow old and grow grey, and never once see that season give way to the next. And during the warmer stretches of the orbit, Pluto's thin atmosphere swells and thickens as surface ices turn to gas. During the colder stretches, the atmosphere may freeze out almost entirely, settling back down onto the ground as a delicate frost. The whole world inhales and exhales, but it does so across centuries. One slow breath, taken over the span of empires. There is something deeply calming, I think, in trying to hold a timescale like that. We spend our days inside small, quick units of time. The next hour, the next morning, the next deadline, the rushed and crowded calendar of a human life. And out there on Pluto, none of that exists. There is only the long, patient turning, the slow glide along an enormous ellipse, a century of darkness easing almost imperceptibly toward a century of faint and distant light. Pluto is not in a hurry. Pluto has never been in a hurry. It has been making the same unhurried journey, the same slow loop through the cold for 4.5 billion years, and it'll keep making it long after every clock and every calendar we've ever built has crumbled into dust. And the worlds beyond Pluto move slower still. The dwarf planet Eris takes well over 500 years to complete a single orbit. The most distant scattered objects take thousands. Out there, in the deep belt, a year is not a unit a mind can hold. It is closer to a geological event, something that happens not within a life, or even within a civilization, but within the slow turning of the solar system itself. When you find your own days feeling fast and crowded and loud, and most days do feel that way for most of us, it can be a quiet comfort to remember that out beyond Neptune there are whole worlds keeping a different kind of time. A vast, patient, unhurried time. A time with all the room in the universe. Let us do one last imagining together, slowly, before the journey turns toward home. Let us set aside the numbers and the measurements and the names for a moment, and simply stand, in the mind's eye, gently, in no danger at all, on the surface of a Kuiper Belt object. Let us feel what kind of place it truly is. You are standing on a small frozen world. The ground beneath your feet is not soil, and it is not quite rock. It is ice, ancient ice, 4.5 billion years old, a mixture of frozen water and frozen gases, dusted with the dark reddish stain of tholins, the slow organic chemistry of an unimaginable span of time. The ground is hard. At this temperature the ice is as rigid and unyielding as granite. It does not give beneath you. It does not soften. It has not changed in any way you could measure since long before there was an earth to stand on. You weigh almost nothing here. The world is small, and its gravity is faint, and you feel light in a way that has no equivalent on Earth, as though the planet beneath you is holding you only loosely, almost politely, ready to let you drift away at the smallest push. A single step would carry you a long, slow, floating distance. A small jump might keep you off the ground for a remarkably long time, rising gently, hanging, settling back down without any hurry at all. You look around you. The horizon is close, far closer than on Earth, because the world is so small that its surface curves away sharply in every direction. You're standing on a little frozen sphere, and you can almost feel its roundness, the way the ground falls away to meet a near and tight horizon all around. Beyond that horizon, nothing, no other world, no nearby light, no companion hanging in the sky, just the close curve of the ice and then the black. And the black is the thing you would never forget. You look up, and the sky is not dark the way a night sky is dark. It is the absolute black of vacuum, a black with no softness in it, no glow, no edge. And against that black, the stars, so many stars, more than you have ever seen, more than you could ever see from Earth, because there is no air to dim them, no haze, no scattering, no light pollution, nothing at all between your eye and the raw light of the galaxy. The Milky Way is not a faint smudge here. It is a vast, blazing river of light, pouring across the whole sky in a band so bright and so detailed that it would stop your breath. There is no wind, there is no sound. There has never been a sound here, not once, in 4.5 billion years. Sound needs air to travel through, and there is no air. The silence is not the quiet of a still night, when you can still hear your own heartbeat and the small noises of a sleeping house. It is a deeper silence than that. It is the complete and total absence of the very possibility of sound, the most profound stillness that can exist. And somewhere in that blazing field of stars you find the sun. You know which one it is because it is the brightest, but it is only a point, a single, brilliant white point of light, casting the faintest of glows on the ice around you, not enough to warm anything, not enough to feel, just enough to see by, dimly, as though by the light of a very bright star. The sun gives you light here. It gives you almost nothing else. And looking at it, that small distant point, that diminished thing, you would understand, in a way no diagram could ever teach you, exactly how far from home you had come. It would be cold beyond any cold you have words for. It would be silent beyond any silence you have known. It would be lonely in a way that the inner solar system for all its vastness never is, and yet it would also, I think, be beautiful, profoundly, achingly beautiful. The stars, the blazing river of the galaxy, the perfect black, the ancient ice beneath your feet, untouched since the beginning of everything. There is a kind of beauty that only exists in places like this, a beauty that comes precisely from the stillness and the age and the silence and the distance, a beauty that asks nothing of you and threatens nothing and simply is, and has been, quietly, for longer than the mind can hold. You do not have to be afraid of that place. It is far away, and it is cold, and it will never touch you. It only drifts out there, slow and patient and perfectly still, one frozen world among countless others, holding its small portion of the dark, and you are here, warm, held, breathing easily, safe in the clearing by the fire, on the small blue world where all the warmth is. Now, let us turn back toward home. New Horizons did not stop at Pluto. After the flyby, the spacecraft kept moving outward, deeper into the Kuiper Belt, and 3.5 years later it did something that had never been done before. On the first day of January 2019, New Horizons flew past Arrokoth, the small, ancient snowman-shaped object of the cold classical belt that we met earlier. We've already heard what its two-lobed shape revealed about how the worlds of the belt are born, but it is worth returning briefly to stand beside that flyby and feel what it actually meant, because Arrokoth was, in every way, the perfect opposite of Pluto, and that contrast was the entire point. Pluto is large enough to drive its own internal activity. Arrokoth is small enough to be utterly passive. Pluto has been resurfaced, reshaped, rewritten by its own geology. Arrokoth's surface preserves the conditions of its formation almost untouched. Pluto is a world with a biography. Arrokoth is a fossil with a shape, and a fossil is exactly what scientists most needed to find, because a fossil does not change, and so it remembers. The images of Arrokoth confirmed what the formation theories had predicted about its gentle assembly. But they also held details no theory had foreseen. The most striking was the flatness. Neither lobe of Arrokoth is a sphere. Both are distinctly flattened, more like thick pancakes than round snowballs. The larger lobe has been compared in profile to a flattened patty, the smaller to a dented walnut. The gravitational collapse models had expected rounder shapes, and the flattening posed a genuine puzzle. Perhaps the lobes were shaped by rotation as they formed, or perhaps the slow loss of volatile ices over billions of years gradually reshaped them after they merged. And the surface offered another puzzle. It was almost completely free of small craters. On most worlds in the solar system, small impacts vastly outnumber large ones, peppering every surface with tiny pits at every scale. Arrokoth's surface was eerily smooth at small scales, suggesting either that the Kuiper Belt contains far fewer small impactors than the models predicted, or that some gentle process slowly erases the smallest craters over time. Either answer carries real consequences for understanding the belt. But the overall impression Arrokoth left was simple and profound. Here was an object assembled gently and then left completely alone for more than 4 billion years. No violent history, no melting. No reshaping by collision, no gravitational disturbance worth the name. Just a small two-lobed body, drifting through the calm of the cold classical belt, preserved with a fidelity that borders on the uncanny, held so still for so long that to study it is very nearly to look directly at the moment of the solar system's birth. Arrokoth also told scientists something about the place it lived. Its survival, its smoothness, its intact and delicate two-lobed structure all testified that the cold classical belt is astonishingly calm. The rate of collisions out there is extraordinarily low. The objects are so widely separated, and they move so slowly relative to one another, that violent impacts are genuinely rare. That is precisely why a fragile structure like a gently joined contact binary can survive, unbroken, for the entire age of the solar system. The cold classical belt is a deep freeze of perfect stillness, preserving its contents with a care that no other region of the solar system can match. And then, as new horizons continued outward through the belt, past Arrokoth and beyond, it began to send back a measurement that no one had predicted. A quiet, persistent signal that may be its most important discovery of all. Aboard New Horizons is a small instrument called the Venetia Burney Student Dust Counter. It was designed and built by university students, and its job is simple to describe. It measures how often microscopic dust particles strike the spacecraft as it moves through space. That dust is not random litter. It is produced by collisions between larger Kuiper Belt objects and by impacts of tiny interstellar grains upon them. So by tracking how much dust it is being struck by, the instrument is, in effect, mapping the density of material in the belt, sensing how crowded each region of the outer solar system really is. The expectation going in was clear and grounded in decades of modelling. The main body of the Kuiper Belt, the region with the highest concentration of known objects, occupies the zone roughly between 30 and 50 astronomical units. Beyond 50, the catalogued population drops away sharply. The surveys from Earth find fewer and fewer objects the farther out they look. So the prediction was straightforward. As New Horizons travelled beyond about 50 astronomical units, it should be flying out of the belt and into emptier and emptier space. The dust counter, sensing fewer and fewer collisions, should record a steady decline. The spacecraft should be crossing from the populated belt into the genuine void beyond it. That is not what happened. Between roughly 45 and 55 astronomical units from the Sun, the dust counter kept registering elevated readings, more dust than the models predicted. The signal did not fade away on schedule, it persisted. Out there, in a region where the standard picture said almost nothing should remain, something was still producing dust. The data, published in a scientific journal in early 2024, pointed toward two possible explanations, and both of them are remarkable in their own right. The first possibility is that the main Kuiper Belt simply extends much farther outward than current models say, that the population of icy bodies does not drop off near 50 astronomical units after all, but continues at meaningful density well beyond that supposed edge. If that is true, then the outer structure of the solar system is significantly larger than we thought. The second possibility is even more striking, that there is a second, previously unknown population of icy bodies out beyond the classical belt, a separate outer ring or an extended debris field, generating its own dust through its own quiet collisions. If that is true, then the outer solar system is not just larger than we thought, but more complex than we thought, with structure we never knew was there. Neither of those scenarios was anticipated by the standard models that have guided Kuiper Belt science for decades. Alan Stern, the lead scientist of the New Horizons mission, described the finding as potentially the first time any spacecraft had discovered a new population of bodies in the solar system. He was appropriately careful with the word potentially, because dust grains carry no return address. They arrive as impacts, registering as counts and sizes, and they cannot by themselves tell you whether they came from a known population slightly farther out than expected, or from an entirely new and uncharted one. But the importance of the measurement does not depend on resolving that question yet. What matters is this. New Horizons is the only spacecraft ever to operate instruments in this part of the outer solar system. It is the only probe collecting original on-the-spot data from inside the Kuiper Belt right now, and the data it is sending back is telling us plainly that the belt is not quietly fading away where the textbook said it would. Something is out there, maintaining collisions, producing dust, extending the structure of the solar system into a region that remains almost entirely unmapped. As of early 2026, New Horizons is still flying. It is in a low-power hibernation mode, drifting through the outer Kuiper Belt, roughly 9.5 billion kilometers from Earth. Think for a moment about what that distance does to a simple conversation. A command sent to New Horizons, travelling at the speed of light, the fastest anything can travel, needs more than 8 hours to reach it, and the spacecraft's reply needs more than 8 hours to come back. To send a message and receive an answer is most of a full day. There is no real-time contact with New Horizons. There has not been for a long time, and there never will be again. It speaks to us across a gulf so wide that every exchange is a slow pair of monologues, each separated from the next by hours of silence. The mission has been extended. New Horizons will keep gathering data on the dust and the plasma of the outer solar system until it finally exits the Kuiper Belt, sometime around 2028 or 2029. And even after that, it has enough power and fuel to remain operational into the 2040s, reporting back from distances beyond 100 astronomical units. There had been hope for a third close flyby, a third small world to visit beyond Arrokoth. But despite years of patient searching with powerful telescopes, no suitable target has been found along the spacecraft's path, and that failure is itself a lesson in the nature of the belt. The Kuiper Belt is so sparsely populated and its objects so faint that even knowing New Horizons' exact trajectory, finding a reachable target requires extraordinary luck and painstaking observation. The spacecraft is threading an immense near-empty darkness, and the odds of another world lying close enough to its line of flight are simply very small. The emptiness we spoke of earlier is not an abstraction. It is the practical reason a spacecraft can fly for years through a belt of countless worlds and never come close to a single one. So New Horizons flies on quietly, alone, the most distant active emissary our species has ever sent, carrying its student's dust counter and its other instruments outward through the dark, still listening, still reporting, still adding faint new lines to a map that remains, even now, almost entirely blank. While New Horizons drifts outward in silence, the work of discovery continues here on Earth, and the Kuiper Belt keeps offering up surprises that no model anticipated. In the spring of 2026, a team of Japanese astronomers working at the National Astronomical Observatory of Japan announced a discovery that genuinely should not have been possible. They reported detecting a thin atmosphere around a small Kuiper Belt object, a body roughly 500 kilometers in diameter, a member of the Pluto family, orbiting at about 40 astronomical units from the Sun. The detection was made using the technique we met before, stellar occultation, the careful watching of a star's light as a distant object passes in front of it. During a rare such event, observed from several sites across Japan, the team watched the background star's light dim and then brighten again as the object crossed in front of it. But it did not dim and brighten sharply, the way it would for a bare, airless body with a hard edge. It dimmed and brightened gradually, smoothly, and that gentle, gradual curve is the signature of an atmosphere, a thin envelope of gas wrapped around a small frozen world. The finding, published in a respected astronomy journal, was startling for one simple reason. By every conventional expectation, this object should have no atmosphere at all. It is small, its gravity is weak, it orbits far from any source of heat. An object like that was assumed to be entirely airless. Until this discovery, Pluto was the only object beyond Neptune ever confirmed to possess an atmosphere, and Pluto is nearly 5 times larger. Even the great dwarf planets, Eris and Makemake and Haumea, show no confirmed atmospheres of their own. And here was a body 1/10 of Pluto's mass, apparently wrapped in a tenuous envelope of gas, estimated to be something like 5 to 10 million times thinner than the air of Earth, and likely made of methane, or nitrogen, or carbon monoxide. How can such a thing exist? 2 main ideas have been put forward, and both of them are fascinating. The first is cryovolcanism, the idea that residual internal heat, deep within the object, could be driving the eruption of subsurface volatile ices, releasing gas that temporarily surrounds the body in a thin, replenished envelope. A small, cold world, quietly venting its own breath from within. The second idea is a recent impact. The possibility that another Kuiper Belt body struck this object not long ago in cosmic terms, excavating subsurface material and releasing trapped gas into the object's faint gravitational grip, where it now lingers, slowly leaking away. And there was a clue that made the mystery deeper still. Earlier observations made with the James Webb Space Telescope had failed to detect the usual volatile ices, methane, nitrogen, carbon monoxide, on the object's surface. If the surface lacks those materials, then the gas making up the atmosphere cannot be coming from the surface. It must be coming from beneath it, which supports either the cryovolcanic idea or the impact idea, both of which draw their gas from below. A scientist commenting on the discovery captured its meaning well, observing that it demonstrates the Kuiper Belt is not a cold, dead place, but a region full of activity, holding many of the building blocks for complex chemistry. The finding hints that atmosphere-generating processes may be far more common among small Kuiper Belt objects than anyone believed, and that future occultation campaigns may reveal thin, fragile envelopes of gas around many more distant worlds. A single discovery like this does not rewrite the science on its own. It is a candidate finding, and it will need confirmation through further observation. But it fits a pattern that has been building steadily for decades. Every new measurement of the Kuiper Belt reveals more complexity, more activity, more surprise than the models predicted. Again and again, the frozen frontier turns out to be more alive than anyone expected, and now the Kuiper Belt is about to be transformed. Not slowly, not gradually, but in a sudden flood of discovery unlike anything in the history of outer solar system science. High in the mountains of Chile, on a peak called Cerro Pachon, a new observatory has begun its work. It is the Vera C. Rubin Observatory, and it carries the largest digital camera ever built for astronomy. Its mission is a project of years, a long, patient, repeated survey of the entire visible sky, photographing the heavens again and again, night after night, watching for everything that moves or changes. For the Kuiper Belt, the implications are staggering. Over the coming decade, the Rubin Observatory is expected to discover something like 35,000 new Kuiper Belt objects. 35,000. That single survey is expected to multiply the known population of the belt by nearly a factor of 10. And most of those discoveries will arrive in just the first year or two of its operation. Think about what that flood of data will make possible. With 10 times as many known objects, astronomers will be able to map the orbital structure of the belt with a precision that is simply impossible today. They will be able to test, properly and decisively, whether the orbital clustering that motivates the Planet 9 hypothesis is a real physical pattern, or merely an artifact of incomplete searching. They will detect smaller and fainter objects, filling in the full-size distribution of the belt and revealing whether its population follows the theoretical predictions or breaks from them in unexpected ways. They will find new resonant families, new dynamical groups, perhaps entire new classes of objects with no counterpart in any catalogue we have today. The Rubin Observatory will even help New Horizons. There is a proposal for a focused micro-survey aligned precisely with the spacecraft's trajectory, hunting for Kuiper Belt objects close enough to its flight path that New Horizons' long-range camera could observe them at relatively close range, even without a true targeted flyby. Imaging a Kuiper Belt object from a distance of just 1 astronomical unit or less would give us data no telescope near the Sun could ever gather. Views of surfaces, shapes, and rotations from angles utterly impossible to achieve from Earth. Put it all together. New Horizons measurements from inside the belt, the Rubin Observatory's coming flood of discoveries, the James Webb Space Telescope's ability to read the chemistry of distant surfaces, and the patient ground-based campaigns watching for atmospheres and rings and moons. Together, these efforts are creating a moment in Kuiper Belt science that researchers do not describe as steady, incremental progress. They describe it as a revolution. The belt is finally crossing over from a dimly sensed outer boundary into a fully mapped, fully characterized region of the solar system, with its own internal architecture, its own population dynamics, and its own ongoing geology and chemistry. And every new finding, without exception, reinforces the same conclusion. The Kuiper Belt is not what anyone expected it to be. It is not a barren scattering of inert ice. It is a complex, structured, in places genuinely active region, one that preserves the earliest records of how planets form, while at the same time hosting processes that are still unfolding today. Its objects carry atmospheres that should not exist. They hold shapes that record events from 4.5 billion years ago, and they produce dust that hints at hidden, unseen populations stretching off into space we have never charted. But there is a dimension of the Kuiper Belt that no instrument can ever fully capture. The data tells us what is out there. The numbers tell us how far away it is. The images show us what its surfaces look like under the faint glow of a sun reduced to a point. What none of it can quite convey is what it would actually mean to be there, to stand in that place, to feel the cold and the dark and the distance and the silence, not as figures on a chart, but as the overwhelming physical reality of an environment so vast that even a spacecraft moving at 14 kilometers a second needs years to cross it. That reckoning is where this journey ends, and it begins with the cold. Before we turn fully toward the cold, there is one more idea worth carrying with us, an idea that lifts the Kuiper Belt out of its loneliness and sets it among countless companions. Our solar system is not unique in having a frozen outer belt, far from it. When astronomers point their telescopes at other stars, young stars, mature stars, stars scattered across our region of the galaxy, they find, around a great many of them, exactly the kind of structure we've been describing all night. They find belts of icy debris. They find rings of cold dust and frozen rubble, encircling distant suns, the leftover construction material of other planetary systems. Astronomers call these structures debris disks, and one of the most famous of them encircles a bright young star called Fomalhaut, visible to the unaided eye from Earth. Around Fomalhaut there is a vast, sharp-edged ring of dusty debris, a structure that is, in essence, that star's own version of our Kuiper Belt, scaled up and lit by a younger, brighter sun. When the Hubble Space Telescope and later the James Webb Space Telescope turned their gaze upon Fomalhaut, they revealed not one belt but a nested set of rings, a layered architecture of cold debris, sculpted, astronomers believe, by the gravity of unseen planets, exactly the way Neptune sculpted our own belt. And Fomalhaut is only one example among many. Debris disks have been found around hundreds of stars. The conclusion the astronomers draw from this is quietly profound. A belt of frozen leftovers is not a peculiarity of our solar system. It appears to be a normal, expected, almost universal feature of how planetary systems are built. When a star forms and planets gather out of the disk around it, there is almost always material that does not finish the job. material too far out, too sparse, too slow to ever become a planet. And that unused material settles into a belt, a frozen ring, an archive of leftover bricks circling a distant sun. This means that our Kuiper Belt is a local example of something cosmic. The story we have been telling tonight. The story of a frozen frontier beyond the last planet, a vast ring of icy worlds preserving the recipe of creation, is not just our story. It is, in all likelihood, a story being told around millions upon millions of stars across the galaxy, each one with its own belt, its own frozen worlds, its own quiet outer wilderness extending into its own particular dark. And there is a humbling thought folded inside that one. If, somewhere out there, around some other star, there is a world with someone on it, someone who looks up and wonders the way you're wondering now, then that someone has their own Kuiper Belt too, their own ring of cold and distant worlds, their own frozen frontier beginning just past their own last familiar planet. The particular arrangement of ice and rock and emptiness that we have explored tonight is ours, and it is precious for being ours. But the kind of thing it is, a belt of leftover worlds at the edge of a planetary system, that is something we very likely share with a vast and silent multitude of other worlds we will never see. Our frozen frontier is one frontier among countless frontiers, and there is something in that thought that makes the dark feel less empty and less lonely and a little more like home. 230 degrees below zero. That is roughly the surface temperature of a typical Kuiper Belt object. On a page, it is just a number, a figure in a margin, easy to read past. But what that number actually describes is a physical reality that no human being has ever experienced, and that no human body could survive for even a fraction of a single second. At 230 degrees below zero, every familiar substance on Earth becomes something unrecognizable. Water is not merely frozen, it is locked into a crystalline state so rigid that it behaves like granite. Steel turns brittle, brittle enough to shatter from a sharp blow. Rubber crumbles into powder. The nitrogen that makes up most of the air you're breathing in and out right now freezes into a pale and translucent solid. Carbon dioxide, the gas you exhale with every breath, becomes a rock-hard frost. Methane becomes a quiet, crystalline ice. At that cold, chemistry itself very nearly stops. The trembling motion of molecules, which is what warmth fundamentally is, slows almost to stillness. Chemical reactions that would proceed in a heartbeat at room temperature become impossibly sluggish, needing millions of years to accomplish what a few seconds would accomplish here. And the chemistry of life, the activity of enzymes, the respiration of cells, the copying of genetic material ceases entirely. Life, as we understand it, is not merely difficult at these temperatures, it is, in any ordinary sense, thermodynamically impossible. And this cold is not a passing season. It is permanent. The Kuiper Belt has existed at these temperatures for more than 4 billion years, ever since the solar nebula cooled and the young sun ignited. Nothing out there has ever been warm by any standard a human being would recognize. Not once, not for a moment. The reason is simply distance, and the way distance starves a place of light. Sunlight reaching a point 40 astronomical units from the sun arrives with only about 1/1600th of the intensity it has here at Earth. By 50 astronomical units, it drops to roughly 1/2500th. These are not figures for a merely dim place. They describe a place where the sun itself, the nuclear furnace that powers all weather, all climate, all life on Earth, has been reduced to a faint point of light that would not even cast a readable shadow on the ground at your feet. So picture it. Picture yourself standing on the surface of a Kuiper Belt object. You look up. The sky is black. Not the soft black of a cloudy night, not the deep blue black of a clear evening, but the absolute total black of vacuum, extending unbroken in every direction. And against that black the stars blaze. They fill the sky in numbers no earthbound observer has ever truly seen, because here there is no atmosphere to soften them, no air to scatter their light, no haze and no glow to wash any of them away. The Milky Way arcs across the heavens with a clarity that would be breathtaking if the circumstances around you were not so profoundly, so completely isolating. And somewhere among all those stars is the sun. You can find it. It is easy to find because it is still brighter than anything else in the sky. But it is not a disk. It is not a circle. It is a point, a single, brilliant, unwavering point of light, no different in size to your eye than the brighter stars surrounding it. At this distance, the sun's apparent width has shrunk so far that your eye simply cannot resolve it as anything more than a star. The object that fills the daytime sky of Earth, that warms your skin within seconds of stepping outside, that drives the winds and the ocean currents and the water cycle and the green machinery of every growing thing, that object out here has become just one more light in the dark. The brightest one, yes, but only that. It is worth lingering on what that transformation of the sun would do to a mind, because it is, I think, the strangest and most quietly unsettling part of the whole journey. Human beings did not evolve in a neutral relationship with the sun. We evolved beneath it, shaped by it, organized around it in ways so deep that we rarely even notice them. The sun fills roughly half a degree of our sky, a real disk, a presence, an object with a visible size. It warms exposed skin within seconds. It marks the passage of every single day with a slow, reliable arc from one horizon to the other. Our bodies keep time by it. Our sleep and our waking are tuned to its rhythm. Our calendars, our agriculture, our festivals, our religions, our art, our architecture, our very idea of what a day is. All of it is built on the daily reality of a large, near, powerful star. The sun, to human consciousness, is not merely an astronomical object. It is the anchor of lived experience. It is the fixed reference point against which everything else is measured. In the Kuiper Belt, that anchor is gone, not destroyed, not absent. The sun is still there. It still holds every object of the belt in its gravity. Its light still reaches these distant surfaces. But its warmth, its commanding presence, its felt reality as a source of life and orientation, all of that has dwindled to something that simply cannot sustain a human sense of normalcy. You would still be in the solar system. You would still be orbiting the very same star your ancestors worshipped. But the star would no longer feel like yours. It would feel like a memory of itself, a bright stranger in a crowd of strangers. That is the cold and the dark together. But there is a third thing out there, harder to picture than either, and in some ways heavier than both. There is the distance, and the silence that distance creates. When New Horizons flew past Pluto, the signal of its success needed 4.5 hours to cross back to Earth at the speed of light. By 2026, with the spacecraft far beyond Pluto, that one-way travel time has stretched past 8 hours. A command sent from Earth in the morning will not reach the spacecraft until the evening. The confirmation that the command was received and carried out will not arrive until the following day. This is not a metaphor for isolation. It is isolation, expressed in the most fundamental terms the universe allows, the speed of light itself. At Kuiper Belt distances, the absolute speed limit of the cosmos becomes a kind of wall. No message, no signal, no beam of light can move fast enough to create anything resembling a real conversation between that region and the inner solar system. Communication becomes a series of monologues separated by hours of silence, each side speaking carefully into the void and then waiting, half a day at a time, for a reply that is already old by the time it arrives. For a spacecraft, this delay is an engineering problem, solved with patient software and careful planning. But for a human mind trying to genuinely feel what these distances mean, the delay is closer to vertigo. We're used to a solar system that feels connected. We watch the feeds from rovers on Mars delayed by only minutes. We see images from the moons of Jupiter returned within hours. The inner solar system, vast as it is, still operates inside a horizon of communication that feels, somehow, manageable. The Kuiper Belt dissolves that comfortable illusion. Out there, the solar system is simply too large for conversation. It is a place where, if you called out, the answer would not come back the same day. The distance from the Kuiper Belt back to Earth is enormous. But there is distance out there that is, in its own quiet way, even more disorienting, and that is the distance between the objects of the belt themselves. We've already counted them. The Kuiper Belt holds hundreds of thousands of objects larger than 100 kilometers, and very likely billions of smaller ones. By any measure of population, it is a crowded place. And yet the volume of space those objects occupy is so staggeringly immense that the gap between any two large bodies is measured in tens of millions of kilometers. Let that contradiction sit for a moment, because it is genuinely strange. The Kuiper Belt is, at the same time, one of the most populated regions of the solar system, and one of the emptiest. Both things are true. There are countless worlds out there, and each one drifts utterly alone. Consider what it took for New Horizons to reach Arrokoth. The spacecraft had to be aimed years in advance with extraordinary precision to pass within a few thousand kilometers of an object only 36 kilometers long, an object embedded in a region where the nearest comparable body might be 50 million kilometers away. New Horizons threaded a needle across billions of miles of empty space to reach a single small body, drifting in a void so wide that to miss it by even a fraction of a degree would have sent the spacecraft sailing onward through pure nothingness for years, encountering nothing at all. That sparseness is one of the Kuiper Belt's most important and most underappreciated truths. The diagrams lie about it, gently and for understandable reasons. To make the belt visible on a page, an illustrator must draw it as a dense band of dots, a crowded ring thick with material. And so the visual impression that lodges in the mind is of a busy place, a place full of things. The reality is the exact opposite. If you stood on the surface of a Kuiper Belt object, and you looked out in every direction, with the most powerful telescope you could imagine in your hands, you would not see another one. There would be nothing to see. No neighbouring world, no nearby light, just the black sky, the blaze of distant stars, and the single small point of the sun. Each object of the Kuiper Belt is an island, separated from every other island by a sea so wide that crossing it would take centuries at any speed we can presently achieve. Compare that one last time to the inner solar system, to the sky you have actually lived under. Stand on the Earth on a clear night, and you can see Venus and Mars and Jupiter and Saturn with nothing but your own eyes. The moon dominates the dark. The sun fills the day. The inner solar system is populated enough and close enough and bright enough that our celestial neighbours are simply part of ordinary human experience. Every ancient civilization tracked the wandering planets with the unaided eye, and built whole systems of meaning and myth around what they saw moving through the sky. The cosmos, to our ancestors, was a neighbourhood, visible, populated, companionable. In the Kuiper Belt, that entire framework quietly vanishes. There are no naked eye neighbours. There is no bright wandering planet to follow across the seasons. There is no nearby moon to silver the landscape. There is only the ground beneath you, and an emptiness so total that the very word neighbourhood loses all meaning. This is the truth the diagrams conceal. The solar system does not fade gently and gradually, from crowded to empty as you travel outward. It crosses a threshold. Inside the orbit of Neptune, the solar system is a structured, populated environment, a place where worlds influence one another across manageable distances, where the sun's energy drives weather and geology and chemistry on world after world. Beyond Neptune, that structure begins to come apart. The objects are still there, but the spaces between them have stretched so wide that each one exists, for all practical purposes, in total isolation. The Kuiper Belt is not a continuation of the inner solar system's familiar pattern. It is the beginning of something else entirely, the place where the solar system stops feeling like a home and starts feeling like an ocean. And here is the part that, for me, lands hardest of all. The Kuiper Belt is not the edge of the solar system either. The Kuiper Belt is vast. The scattered disk beyond it is vaster. But beyond even the scattered disk lies a structure so much larger than anything we have spoken of tonight that it changes the meaning of the word solar system altogether. It is called the Oort cloud. The Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. It is theorized to be an immense, roughly spherical shell of icy bodies, completely surrounding the entire solar system, surrounding the sun, the planets, the Kuiper Belt, all of it, at distances ranging from perhaps 2,000 astronomical units out to as much as 100,000 astronomical units from the sun. If the Kuiper Belt is the porch of the solar system, then the Oort cloud is the distant property line, a boundary so far away that it stretches a meaningful fraction of the way to the very nearest star. The Oort cloud has never been seen. No telescope has ever resolved a single individual object within it. Its existence is inferred entirely indirectly from the behaviour of the long-period comets, the comets that take not decades but millions of years to complete a single orbit, and that arrive in the inner solar system from random directions in the sky, from every angle, with no preferred plane. Comets like that must come from a vast, roughly spherical reservoir at extreme distance, and the Oort cloud is the name we've given to that reservoir we cannot see. Estimates of its population range from several 100 billion to a few trillion icy bodies, though most are thought to be small, perhaps only a few kilometres across. If the Oort cloud exists as the models describe it, then the sun's gravitational domain extends more than a light year out from its centre, more than a light year of frozen debris, faintly bound, drifting in the dark. The nearest star to our own, Proxima Centauri, lies just over 4 light years away, which means the Oort cloud, at its outermost reaches, extends a significant fraction of the entire distance to the next star system. The solar system, properly defined to include everything the sun's gravity holds, is not the compact arrangement of planets that fits on a classroom poster. It is a structure measured in light years, a sparse, enormous halo of ice, reaching so far that the sun can barely hold it. A passing star, or a gravitational tug from the slow turning of the Milky Way itself, can dislodge an Oort cloud object from its orbit and send it tumbling inward on a journey of millions of years toward the inner solar system, or outward into interstellar space, gone forever. And here is where the Kuiper Belt finds its true place in the story. The Kuiper Belt sits at the innermost margin of this enormous outer domain. It is the last structured region, the last place where distinct families and orbital patterns can be mapped, studied, and understood. Beyond it, the scattered disk thins into a diffuse haze, and beyond that, the Oort cloud stretches off into theoretical territory that may never be directly observable with any technology we can currently imagine. This layered architecture reveals something genuinely humbling about the true nature of the solar system. The warm, bright, geologically active zone that humanity knows and has studied for thousands of years. The zone holding Mercury and Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune occupies a vanishingly small fraction of the Sun's total realm. Let me try one last image to give that its proper weight. Imagine you could shrink the entire solar system all the way out to the outer edge of the Oort cloud until it fit inside a sphere the size of a large sports stadium. Shrink the whole thing down to that size. On that scale, with the Oort cloud forming the outer walls of the stadium, the entire planetary system, every world from Mercury all the way out to Neptune, would occupy a volume no larger than a single tennis ball, resting quietly on the grass at the very centre of the field. That is the proportion. That is how much of the solar system the familiar part actually is, and consider that proportion through the one object we've ever sent out into that wilderness. New Horizons left Earth faster than any spacecraft before it. It crossed the orbit of the Moon in 9 hours. It reached Pluto in 9.5 years. It passed Arrokoth after 13. As of 2026, it has been flying for 2 decades at more than 14 kilometers per second, and it has reached about 64 astronomical units from the Sun. It will leave the Kuiper Belt around 2028 or 2029, roughly 23 years after launch, and at that point it will only have crossed the innermost fringe of the Sun's true domain. The Oort cloud begins at around 2,000 astronomical units. At its current speed, New Horizons will not reach the inner edge of the Oort cloud for roughly another 700 years. It will not reach the outer edge for something like 30,000 years. The fastest spacecraft our species has ever launched will spend 7 centuries merely approaching the threshold of the solar system's real boundary, and 300 centuries crossing it. That is the scale of what lies beyond the Kuiper Belt. And the Kuiper Belt itself, the structured, populated, scientifically reachable part of the outer solar system, the part this entire journey has been about, is merely the doorstep. So let us gather all of it together now, gently, the way you might gather your thoughts at the very end of a long day, before letting them go. The familiar solar system is not the solar system. It is the innermost core of the solar system, a small, warm, well-lit room, surrounded by an ocean of cold and dark and empty space, extending outward for trillions of miles in every direction. And the Kuiper Belt is where the transition begins. It is the threshold. It is the boundary zone where the orderly, planet-filled inner system gives way to the sparse, frozen, almost unimaginably vast outer wilderness that makes up the true bulk of the Sun's kingdom. This is what the strange, slightly unsettling feeling at the heart of this story really is. The Kuiper Belt does not frighten because it contains some single monstrous object, some specific threat hurtling toward us. There is no such thing waiting out there for us. The feeling is something quieter and stranger than fear. It is the vertigo of scale. It is the disorientation of realizing that the solar system you always thought you understood was a small, warm, well-lit room, embedded inside a structure so large that you cannot see its walls. Think about what that means for every map of the heavens ever drawn. Every civilization that ever looked up and tried to chart the sky was charting the inner room. The Greeks saw the planets and called them wandering stars. Copernicus placed the sun at the centre and set the planets circling it. Kepler refined those circles into ellipses. Newton explained the gravity that holds them. 4 centuries of telescopes catalogued moons and rings and atmospheres. Spacecraft visited every planet in turn, and the solar system came to feel known. It came to feel mapped. It came to feel, in some quiet and comfortable way, finished. The Kuiper Belt ends that feeling. It reveals that the mapped portion of the solar system accounts for only a tiny fraction of the whole, and that the rest is frontier, unexplored, and in much of its extent with our present technology, simply unexplorable. We have not explored most of our own solar system. We've explored a small, bright core and mistaken it for the entire structure. And yet, and this is where I want to leave you, because it is the gentler truth and the truer one, there is nothing in any of this to be afraid of. Yes, the Kuiper Belt is cold beyond any cold a human being has ever felt. Yes, it is dark and vast and silent and empty in a way that erases every familiar landmark. Yes, it dwarfs the warm little planetary system in every physical dimension you could name. But it is also quietly and completely ours. It belongs to the same star that rises over your horizon every morning. It formed from the same cloud of gas and dust that became the ground beneath your feet. It obeys the same laws of physics, and its frozen worlds are built from the very same elements that build your body and your bones and your blood. The Kuiper Belt is not an alien place intruding on ours. It is the far country of our own home, the distant unlit wing of the same house, and it is not lifeless in the way dead suggests. It is a place that still works. It still sends comets sweeping inward to paint our night skies with ancient ice. It still produces dust, filling its dark reaches with a faint haze of microscopic particles. It still holds worlds that may keep liquid water in hidden seas, and worlds wrapped in atmospheres that should not exist, and snowman-shaped fossils preserved so perfectly that to look at them is to look directly at the morning of creation. The Kuiper Belt is a frontier that is somehow ancient and active at once, finished and barely begun, frozen and alive, and we are learning it, slowly, patiently, world by faint world. The Vera Rubin Observatory will soon multiply the known objects of the belt tenfold. New Horizons drifts onward in the dark, still listening, still reporting, until it crosses the belt's far edge near the close of this decade. The James Webb Space Telescope reads the chemistry of distant frozen surfaces with a precision that was pure fantasy a generation ago. And patient astronomers scattered across the Earth watch the flicker of stars for the faint shadows of worlds too small and too far to see any other way. We are reaching out gently into the cold, not to conquer it, but simply to understand it, to know our own home, all of it, even the rooms where the light has never reached. So here is the thought I would like you to carry down into sleep tonight. The 8 planets orbit in a warm, bright, compact clearing. A small circle of firelight in the middle of an immense and frozen forest. And the Kuiper Belt is where that forest begins, not at some impossibly distant edge, not at the theoretical boundary of the Oort cloud, a light year away, right there, just past Neptune, just past the last familiar landmark. The solar system, you know, quietly gives way to something colder and stranger and older and far larger than almost anyone is ever asked to imagine. But a campfire is not a small thing because the forest around it is large. A campfire is the place where the warmth is. It is the place where you can see the faces of the people you love. It is the place where you are safe and held and home. Our solar system is mostly cold and mostly dark and mostly empty. That is simply true. But we do not live in the cold and the dark and the emptiness. We live in the clearing. We live by the fire on a small blue world, the third light from a sun that still fills our sky and warms our skin and marks our days. And tonight, knowing how vast and how frozen the dark really is, that small warm clearing does not feel smaller to me. It feels more precious. It feels like exactly the right place to be. So let the rest of it go now. Let the cold worlds drift on in their slow, silent orbits, as they have for 4.5 billion years, as they will for billions more, needing nothing from you at all. Let the great frozen forest stand quietly around the edges of your mind, and let yourself settle here, in the warmth, in the clearing, by the fire. You've travelled a very long way tonight, out past the last planet, through the frozen belt, all the way to the trembling edge of the sun's domain and back again. It is a long road, and you have walked all of it. Now there is nothing left to do, nothing to reach for, nothing to solve, just rest. The dark out there is old and patient, and it is not waiting for you. It asks nothing of you. It will keep exactly as it is until you wish to return to it. But for now, close your eyes, let your breathing slow, let the warmth hold you, and drift gently down into sleep.